anybody else in town, but I'm hoping that everybody can meet us there for, it's a nice view. It should be nice weather. So if you like skin tone, there's umbrellas to hide under. But it's a neat place, and they do have some happy hour and snacks. Can you hear me? Can you still hear me? Okay. Okay, so I get to do kind of a fun talk because I get to talk about everybody else who's demoing today, and not everybody has a demo here, but it's kind of fun to see how the community is evolving and growing as a group. And so I'm going to go over a little bit of some things that the community is doing, some things that USGS is doing, and if I have time, I'll go into a little more detail about some other things on the horizon. I don't think I'll have time to get there. Basically, the outline community examples kind of state of the art where we are with focusing on that GIS mapping aspect of things. I'll look at some online GIS data resources that the community is also community driven. I'll look at GIS applications update. So outside of the web environment, what are the desktops looking like and what are some changes to that? If I have time, I'll go into kind of highlighting some of the foundational data products that have been recently released by the community. And also, hopefully, we can get input from things I don't know about. I don't have time for the community sensor model, but I always throw extra in there. So who am I? I'm Trent Mayer. I've been at the USGS for 28 years. I now run what's called the Mercator GIS Lab. Coordinate standards and mapping and geologic mapping, kind of the technology of the technical side of that. They're now funded by the NASA PSDI. Fix that. Kind of the infrastructure. It used to be funded by PG&G. So basically, this is strictly unfunded to facilitate geologic mapping, but we've been able to use this umbrella project to facilitate community mapping. I think NASA finds that perfectly happy with that. So our history with GIS is we started to do GIS conversions in the East, and that was specifically for converting contour maps to a GIS format. So we got into GIS just to do vector conversions. We started to actually do GIS for geologic map production in the 90s also, and then we started to do lighting site analysis and online mapping in the late 90s. So why do we use it? Why do we use this GIS thing? Well, it allows this thing that we do, that we all want to do, data or overlay and analysis. Obviously, is key. So as the planetary GIS domain, what are the needs? It really is the same as Earth-based mapping. If we're talking about as far as spatial infrastructure, we are learning from the Earth community. Projections. We fought over this for Mars. We still are fighting with it for Mars. But we need to have those common projections for the archival data sets. We need the data to be accurate for robotic and human missions, just like we do on Earth. We need support for huge data sets. We do have terabyte mosaics now. The 16-bit Kaguya mosaic is a good example of that. We need data portals and we need metadata. That's a common theme that I've heard throughout this conference, is that data discoverability tools, not just PDS search engines, but search engines that facilitate data outside of the PDS. standardized formats, and that's a big common thread in the Earth community also. Online mapping services is continuing to grow. Interoperability, those keywords for work, and then we're starting to get into the true 3D surfaces. Do you guys want to load lower? Do you guys want to load what? You can pop down the number 4. It's on the little red line. Okay, now you guys can go. So what we're talking about tomorrow is this thing called planetary spatial data infrastructure, and one of the tenets is spatial data should just work. So that's a loaded statement. And so I have several examples from this meeting about topics of why we want to make this statement more true. We can never make it fully true, but so one of the examples I've talked to a scientist, and I was excited, and I was like, you know what? We got this new mechanism. We can create an ISIS label pointing into a geotiff. And I was like, this is the best thing. This is awesome. We can make a PDS4 label, point into the geotiff. And the scientist looked back at me and goes, I have no idea what you just said. Can I find it? And can I load it? And so to me, that kind of hit home as something as this. That was, oh, we've never been able to do this before. They could care less. They just want the data to work. They don't care about the detail. So it smacks you in the face that as engineers, we keep on engineering things for us when we need to make sure we're engineering it for the scientists. Another one was, I have a list of images, and how do I just want to see the images. I just want to see I want to find them. I don't really want to download them. I just want to view them. And so we went through and we were like, okay, we can do that. We can write a little program. You can download the footprints and we can organize it and we can pop it up and make a virtual mosaic. What I did there was make the scientist a data scientist. And again, they want to be a geologist and a spectroscopist. They don't want to be a data scientist. So I just inserted the idea that they have to take this list and write a program to be able to do how, as we as a community, can facilitate the science, not make everybody a data scientist. So the last one was in the neural network talk that Hannah gave. One of the first things she changed in her slide was to make her successful, she needs the data accessible. Make the data accessible so that she can work on her neural network training. She can do the data sets. She doesn't have to worry about where the data comes from. And so that again is kind of this whole idea that spatial data should just work. How do we as a community go from a data-driven PDS of you have to find it within the PDS to data as a service that I can just use? So if I look at where we are as a community as far as infrastructure, I think we're probably about there on this mountain, and so we have a long way to climb. Now, I will say that we've made a lot of changes in the last 10, 20 years. It is easier to use. Generally, you can drag it into applications. It works, but we still got a long way to go. So now I kind of get to just go over some examples. These are what I would call kind of a state-of-the-art summary. I'm not going to go over all of them to understand that folks are working on these. And again, we need to make sure that we continually check with the scientists to figure out how to become a data scientist to use these. So examples, Planet Server, and I'll have pictures for these. That is a hyperspectral data cube type visualization, and it streams data live. It's done by Jacobs University, and it's part of an OGC standard, which is great. A custom WMS engine and processing server, Arizona State University. We have JPL working on Mars Trek, Moon Trek, and Vesta Trek, their WTMS applications and servers. 3D interface using cesium. Mars has been a staple for a couple decades, and mission planning, data viewer, Arizona State. So a great example of a GIS. I don't know if Lucian's here, but Esri is currently working on, they continually to tweak their server infrastructure. How do you serve this data more optimally? Quicker, how do you make terabyte mosaics instant? They actually are supporting the planetary community as putting some test WMSs on their Amazon cloud as cloud services. All their code that they're releasing for their cloud services are open and work in GDAL also. So even though Esri is a commercial company, they're supporting the open source community for optimization of these services. Best of image bases and the WFS nomenclature, we try to maintain the best of data from the community as a WMS and WFS. And so whenever there's a new base, we'll make sure that we try to get that online to use in your own application. The DLR and the Fry University are always looking at the WMS. They're supporting open applications like GDAL for Wicker, but the same thing. I would say that the Chinese have a WMS tile cache. I'm sure the Indian Space Agency is also looking at that too. So to get into some pretty pictures, the WCPS server supported by Jacobs gives you access to hyperspectral data. This is Prism. You can plot it, you can find it, I can bring it into my mapping interface. IMARS from the Fry University, we have a talk about this. They're actually looking at how do we make these services more dynamic? How do we load data in the back end? Generally, we think of WMS as static base tiles or static mosaics. How do we actually make WMSs a little smarter? We have the JPL Vesta Trek, so 2D and 3D interface, data discoverability. Could any one of these be better? Yes, but these are, we're going to have to make sure that we're supplying what the scientists need. So hopefully these will evolve as we hear feedback. AMARS, again, advanced streaming techniques. We've had that for a long time. Client app, so it's a download, which means it can do a lot of things. Store locally, download shape files, digitize. This is showing some of its human mining site capabilities that have been recently added. Here's the list of 30 plus different planetary bodies with 100 plus WMS layers. So again, we will try to make these available at time of release. So we're updating the messenger mosaics that were just released in May, and that should be available from our WMS, and we hope that other people put those into their servers too. This is the tile cache that is hosted by Esri on the Amazon cloud. Highly optimized. I believe this uses this new format called MRF. We call it SMRF. With this new open LORC compression. Don't need to get into the details, but kind of a new way to think of how to optimize these back-end services. Cesium, this is done by our colleagues at the Paris Sud University. I happened to work with them last month. Had a great trip over there. They were able to bring in all those WMSs I was just talking about, those mapping layers, into a single cesium viewer. They've added a bunch of planetary tweaks to cesium, and they posted those tweaks onto GitHub. So all that source code to make cesium planetary savvy is available. And now, because we have these back-end servers, we're starting to see cell phone apps come out of the public, which is great. So this is an example. Actually, forget what the Android app is called, but there's one for Mars, there's one for Venus, one for the Moon, and this relies on these live dynamic services. streaming challenges, I've been talking about this thing, WMS, web mapping services. There's still a lot of work to do. We still have to, it is very much of an Earth-based standard, and we're still working with the standards body of the Open Geospatial Consortium to make sure it works for planetary. Because we originally supported these planetary codes on the DPL server, but it's nice that LunaServe also implemented them. When we talk about tiled WMS, there's still a little fragmentation in the community on the Earth side also, so that needs to be ironed out. And then bandwidth limited services, WCPS, WCS, WFS are, how do we make these work? Because they take up a lot of bandwidth, they're slow, so those are still evolving. Just a brief overview on kind of astrogeology, if I can spell that right, online GIS resources. I didn't want this to be the USGS show, but whenever we have an online site like the IAU Planetary Gazetteer, we will try to make it some kind of GIS accessible layer for it. So for every single body, there's a shapefile that's updated nightly. So when 20 new names come in for series, that night, once they've been approved, they'll show up in a shapefile that you can download. If you're clever, you could have that a cron job and bring that down nightly yourself. So for pilot, the geoscience node has this also. Basically, it's a footprint viewer. I don't mind having multiple viewers for these things, and we can kind of feed off of each other on who we should do that better because they're doing it better. Oh, the pilot's doing it better over here, so we should emulate that. But again, just like the geoscience node, nightly GIS shapefiles are created from the footprints that you can download and use. For POW, we'll have a demonstration of that later today. It's essentially trying to make ISIS more accessible. We don't want you to have to learn how to run ISIS every time. So this application runs ISIS for you on our cluster. Not many options. It's already complicated enough. But basically, the end result is GIS-ready images. It doesn't mean that they're controlled. It just means that they're GIS-ready. And we have this evolution of MapAPlanet. The real change in MapAPlanet for this next release was to make it simple to upload the data. And so the primary key for me was to make sure that I can just get access to the full res mosaics nonstop. Just give me the mosaics. But we can also jump into the interface and extract areas and order a different map projection or a different format too. We have a lot of targets. Almost anything within the MapAPlanet interface should be also available live in the WMS mapping layers too. So a lot of these things, the open layers, we saw that there's tweaks to cesium, there's tweaks to these leaflet engines. Hopefully, as a community, we need to make sure that these tweaks are pushed on GitHub or available somewhere so that if someone wants to use open layers, they can download our tweaks and use them directly instead of rewriting them. So this is just an example that planetary extensions for open layers made the source code available. We need to do that because we've upgraded the version 3 of open layers, so we need to make sure that code gets out there. And then something that we've been actively working on in association with the PDS is this idea called the PDS Annex. What we're trying to do is find a PDS equivalent archive to host GIS files, to host geologic maps, to host things that have an association with a PDS archive, but don't belong in that archive. Like, and so I think I'll actually stop there. And again, one of the things that as a community, we've done a pretty good job, that there's been a lot of things kind of, we're bouncing, you'll see a lot of interfaces starting to use these things called leaflet and open layers. And so we aren't inventing the wheel as much as we used to, and that's a really good sign. So as we're climbing that mountain, I can see that we're starting to share more components. We're starting to understand that we need an infrastructure to realize tools. Tools need to be associated with a scientific use case so that we're not just building it because it's cool. And I think that's it. There'll be plenty of other presentations talking about a lot of these tools. You see this new tool, think about how it fits into the grand scheme of things. I'm afraid of having a lot of tools out there. What I am afraid of is that we all have to be data scientists to implement those tools, or to implement that training set, that neural network. So I'm hoping that tomorrow we can talk about these. What do we need as a community to support these tools in infrastructure? Thank you.
All right, so our next talk will be not by Sebastian Walter, but by Christian Riedel. He'll be talking to us about dynamic web services for single images. And also, just so you know, at 5 minutes before the end of your window will be the first beep. At 3 minutes before the end of your window will be the second beep. That's probably when you should be wrapping up. And at 1 minute before the end of your time window, I will stand up and start walking away.
Okay, good morning, everyone. So this is a talk I'm giving for my colleague Sebastian Walter, who unfortunately couldn't be here today, and it's about present images or a time series of images on the web as part of the IMAS project. Okay, let's start with an introduction to the IMAS project. IMAS is an EU-funded collaboration which is dedicated to surface changes on Mars. And the idea is to have a web service. The data that has been collected by NASA and ESA since the 1970s can be analyzed. HRC data is set as a geodetic basis. All the other data has to be co-registered to HRC. And so far, my colleague Sebastian was successful with co-registering mock CMIS, CTX, and high-rise data. So these data are already available within the WebGL. Also part of the IMAS project was an automatic change detection within the cloud and change evaluation by crowdsourcing. So WebGL can be accessed via this URL, and it's based on OGC standards such as WMS, WMST, WMTS, and WCS. Look at the WebGL system design. There's the front end and the web end. The front end consists of a browser and the data that is handed to the browser via HTML and JavaScript. And the back end consists of a web server with the file storage raster data attached and databases for storing geometries and metadata attached. In between the web server and the browser, there's the tile cache instance, which is used in order to speed up the whole display process of raster data. At the moment, the whole servers are located on one physical machine, but in practice, they could also be located on different machines for load balance purposes. So this is an example that Sebastian did to generate dynamic layers via vendor parameters. So this is what the URL looks like, and there's an OGC getMap request, and there's an additional vendor parameter, which is product ID parameter added in the PDF. So if the user calls a layer like that, the layer is dynamically created in the backend and then handed over to the client. Okay, so let's look at the front end, the user interface. So IMARS works with open layers, so there are existing modules of open layers that were used, but there were also new ones created. So for instance, for the here, where the user can select raster files according to Earth or Martian years. That was a new module was created for that. There's also a lat-long switcher here, full screen mode, zoom controls, projection switcher where the user can switch between projections which are centered to the North Pole, South Pole, or to the equator. There's a layer switcher here where the user can take raster data that is in the background, also with the transparency slider here. And there's a toolbar for single image workflow up here. This toolbar can be used to visualize the time series of single images. So there are up here and the bottom bar there. And I think the workflow is still undocumented on the website, but the general idea is that the user should these buttons in a reading direction, so from left to right. And the top one can select layers of interest and add them to the WebGIS. And in the bottom bar, one can navigate through this series of raster data. So to give you an example how that looks like in the WebGIS, image of a crater on Mars, and we are interested in how this dark material here on the crater floor has evolved or changed over time. What we can do as a user is first we select the data here that is available. So that's MOC, CDX, TMS, and HRFC, and then the footprints of the available data are displayed. So with this button, we click on the dark material here, and then all the footprints which intersect this point are selected. Then using this button, we can add the footprints as layers here. So, and these layers can be sorted according to the timestamp of the data or alphabetically. Now they're sorted according to the timestamp of the raster data. When we switch off the footprint, the outlines of the footprints, we can start the animation, and we can see how the dark material has changed over time using these data sets. To go through these alphabetically, and currently it's sorted according to the timestamp. Okay, so this is an example on how to visualize a time series of images on the web to visualize the changes, the surface changes on Mars. Okay, so WebGIS can be accessed via this URL, imars.planet.fu/berlin.de. And I'm already done with this now, so we still have time for questions. Again, I'm not involved in this project, but still, if you have questions, I'll try to answer them as good as possible. And yeah, for detailed questions, you can contact my colleague Sebastian Walter via this email address. And if you don't have pen and paper with you, you can also approach me, and I'm happy to get you in touch with Sebastian. Thank you.
Is it true? Is IMARS the project's done, right? Or is the funding over?
Good question.
And I think it is. I think it is. But I guess something we'll have to bring up with Sebastian is how does he think he can maintain this as a viable engine? That's a really good. That's a unique capability that not many people have. Is a capability to do dynamic loading. So I'm hoping that there's a long-term kind of sustainability. If you have any thoughts on if he has plans to keep this alive for a long time.
I hope so. It would be great.
Okay. That's not my interest.
Yeah.
Edinburgh University of Tennessee. This is on. Anyway.
Oh,
so-
Go ahead and flip it on
should be a button on
the
top,
top.
which
Yeah,
has been
we just
challenging for people.
give us 2 seconds.
Great, thank you. Thanks for that interesting talk. I was wondering what kind of analyses, if any, could be done in that front end, say the ones, when base one sees some change, but would like to sort of quantify it or do some analyses, some simple analyses of the image to try to test if there's actual change or how much change there is.
I think that's part, I'm not 100% sure, because again, I'm not involved in the project. I think that's part of the change detection that's going on in the backend. So Sebastian's part is only the visualization part. So I guess that could be something to work on, the automated part, and then have it analyzed visually by the user.
Thank you.
Great.
I'm Ray Arvidsson, Washington University in St. Louis. This is kind of a comment that transcends this presentation in 2 points. One is I totally agree with Trent that having a lot of work done by individual groups just indicates kind of rich diversity and capabilities that are being developed. But some of the capabilities will be developed and then dropped. Some of them will be supported for some period of time, maybe short, maybe long. I'm confused by the number of possibilities for using these services. Do we need a clearinghouse? You know, a list of what's available and what their purposes are and what the capabilities are, either by the PDS or by the survey.
Do you mind if I?
Please, yeah.
So
during the initial developer session yesterday, I cornered several scientists, Ross included, and every single one of them, and I've had these conversations over the last year with NASA headquarters too, every single one of them said data discoverability is critical, and we don't have a good solution yet. Right? And so, yeah, do we need a clearinghouse? Yes. Do we need to have a clearinghouse that says, this is the base you should register to? I think we should, but I don't know who has the authority to put a stamp, the gold star on, right? You should register everything to MOLA. We know that, but how does someone coming into the field know that?
No, I mean something different.
Okay.
So there are 10 different capabilities that offer different kinds of services. Coming in, wouldn't have the foggiest as to where to start, what to now, or whether or not they're actually operational. By clearinghouse, I mean a list of what's available,
Yeah.
how to get to them, service they offer. I mean, for example, the analyst notebook and ODE, they really serve to find and download data. And they're different than JMARS, different than Pilot, different, I think, than everything we're going to hear today. But I can't keep track of everything that's going on. But I think it's wonderful. For the very reason you said, we're not there yet in terms of discovery-driven science and how to do it. But it would be useful either for you or for me just to put together a list that we update that can be accessed by people outside of developers.
And, you know, I made the point that I don't mind the kind of the proliferation of all these tools because it helps it just helps us evolve as a community to make better things. But I think that something we haven't done service to is this is a prime example of a really good use case for dynamic. So maybe we should have a list that says, okay, this is where you go for that dynamic use case. Because we're all generating these, we all have that basic functionality at the forefront, and that makes everything confusing. I think we do need to focus as a community on what am I getting out of this interface? Why are there 10 that look almost the same? Right? Why? And so hopefully we can, again, that interface is they all have similar functionalities, but hopefully each interface has a unique capability, and we need to make sure that the user knows what that is.
Exactly.
And if we are having these things that are almost the same, then we should probably figure out how to merge them together. Right.
I'm sorry, that's
So-
not a question for you.
Yeah, well, no, it's a good discussion topic because I think the tools need to have a focused use case. Tools as long as it has a focused use case.
Any other questions for Christian about MRs? So I've got one in case anyone else is thinking about it and on their way to the microphone. So you indicated that HRSC is the geodetic base.
Yeah.
But I assume that what that really means is it's HRSC that's been controlled to MOLA is the base, not just HRSC relatively controlled to itself. Do you know?
I don't know.
It's
Sorry.
okay.
Let's assume that
Yeah, I
Sebastian did
think,
the
I
right
think,
thing.
I think it's that way, yeah.
All right. Do we have any other questions for Christian? All right, awesome. Christian, can you pass the mic? And actually, now we still have some time. And so if anyone has any questions for Trent, because he fills up his whole time, now would be a good time to bring that up. And actually, to follow on to the discussion, I think to what Ray was saying, right, it'd be great if we had some sort of clearinghouse, but I think we're still probably a ways from that, and there are great questions about who's responsible for that sort of thing. But this kind of description about tools and data, it might be useful, and I think that Trent, you or the USGS is probably the right group to maybe do like a yearly, this year in GIS, these are the tools that are still functional, this is what they do. I don't know how easy or difficult that would be, but Ray has a point, it's always changing. And when we get new people to come into the field, some of the problem is that one person's got a tool, pardon? Even old people, that's true. And so, you know, you get siloed yourself, right? Someone who's been doing something for a long time has a favorite pet tool and may not know about the new tool that does the great thing. I've learned a lot myself this conference about tools that have existed for a year or more that I didn't know about. And so a better discovery mechanism, and I don't know what that is, but more information and more communication about tools and services.
I guess the only thing I was going to raise, sorry, we're not on the mic. I really enjoy, there used to be a publication.
You can come to the mic.
Yeah, that's fine. There used to be a publication on kind of the state of the open spatial GIS that a fellow from Canada used to publish every year or every 2 years. And I think that's a really good idea to have kind of a paper or a video to say, here's what's happened in the last year or two, and kind of a state of tools, state of data.
I think that'd be great. Yeah.
Yeah, I have one, Lucid area from University of New Mexico. I have one quick question. I've heard lots of talk, the entire conference on spatial infrastructure, okay? But we just heard talk about temporal data. Is there any provision for spatio-temporal databasing and building in that aspect? Because I haven't seen that at all. Just comments.
So really,
That's a great, Grant, you want to come back up here?
No, I'll just say that it's a big focus right now in the geospatial community. They're tackling that, and so it's a big topic, and it's not solved very well.
Right, and GIS systems typically don't deal with time very well. So yeah, it's I look forward to something coming up so we can actually look at change and actually incorporate it into the databases that we have.
Yeah, so I mean, there are ways certainly to, you know, from the, as Trent says, you know, from the data scientist perspective, there are ways, of course, to time tag things and to analyze those things. But kind of analysis-ready systems that make it easy for a user to do that are still lacking, even in the terrestrial community. And even now that community is more interested in that and how forests change and time series in earth science data. So that community is certainly tackling that problem. And it's probably, well, it's probably cheating to say, we hope they just solve it and then we can use whatever they figure out. But certainly we'll take what they solve. Name and
Oh, yeah, sorry. So my name is Andrew. I was at Johns Hopkins. Before I started my program, I worked on a spatial temporal database, actually. And I still am technically a member of the Location Tech CLIPS Foundation working group. These are problems that are not entirely solved yet, even on the Earth side. And I think some of the constraints on the planetary side, in terms of budget, we definitely need to work off what they're doing. So some of these problems are not solved yet. But if you're interested in these problems, definitely check out things that Location Tech is doing if you're a developer or making capabilities in the planetary science community, because there's a number of open source tools that that implement these sort of backend databases in terms of the time queryability of this geospatial data that may be applicable. I think the interfaces that we have it's good that we have them. I think there needs to be there's sometimes not a separation between the backing databases that make these analytics capable themselves and the front end user interfaces. So these are reinventions of the user interface as you need to, because these actual algorithms and analytics require a more sensitive GUI to use them. I think one place where you can start to pull things together is certainly on the back end, and people could have different front ends for that. And so I'd encourage people to keep an eye on OGC and new standards they publish, and for people who use those. So, yeah.
All right, you have something quick, Fred?
Just say so we've been talking about this, the PSDI, right? Essentially infrastructure. And so we should think about, who's in charge of what data set and make sure that they're serving in a way that we can all access it. So they've got the database, it's all set up. Great. Now that's part of the spatial infrastructure, then high-rise team can have their spatial infrastructure, just as long as we have that connection of, what standards they're using, so we can get back to our tools. Then I think we've got that in place. But we should think about, whether we want separate data warehouses, or do we want to build a conglomeration for the planet, right? But anyways, yeah, I think in terms of interfaces, I think it's also like you were saying, Trent, get back to what the user wants. I think we design, sometimes as a computer scientist thinks we want a map to be viewed, and not as a user wants to view it. So how does a geologist want to draw a cross section and scale it, do all these things? No, they want to, they want to click 2 points and get something.
All right, great. So now we have Ramiro Marco Figuera, who is going to talk to us about climate change.
So, hello everyone. Sorry for my voice, but the air conditioning is killing me. So I'm Ramiro Marco Figuera, the lead developer of Planet Server. I'd like to thank BAN, our engineering solutions, Anik, Halder, and Kyo and Yin, it's vice versa students, working with me, and Angelo Biorosi, which is the project manager of Planet Server. So, what is Planet Server? Planet Server is part of the Horizon 2020 Earth Server project. We are the planetary science data node, but we have the PML, Plymouth Marine Laboratory, serving oceanography data, MEO for meteorological data, site data solutions, also meteorological data, Jacobs Uni, Razaman provides the database system management, NASA provides the web window visualization that we use, and then NCI collaborates with us, together with MEO, to show Landsat data. So, how do we divide Planet Server? So we have the server part and the client part. So everything in green is done in the background. Everything in red is done live in the client. So first of all, we download Prism, TRDR, and MRDR, and MCube data. We download it directly from PDS. We pre-process them using MB, and then we transform them into GeoTIFF using GDAL. And then we use so-called ingredients to ingest them into the database. It's called Razaman. We plug the client in, which are 3 different clients, I'll show you later. And you can visualize and you can analyze data by using the OGC standard WCPS. Have any one of you heard about WCPS before? Awesome. 1, 2, cool. That's a user number, so don't worry. So what's Razaman? Razaman is a database management system, which is, long story short, basically you can store your ND arrays together with their reference, the coordinate system. It provides a query language, so you can query the coverages or the data that you ingest into your database management. The thing is that the array it's partitioned automatically when you ingest them, and thus decreases the processing time actually. And then when you want to query, it really fast compared to other services. So WCPS WCPS is basically an enhanced WCS. I'm showing you, so it has three parts basically. So the service endpoint, whatever you see in red, the request type in green, in blue. This example query here is from ECMWF for two main reasons. One reason is that if I show you the WCPS queries that we use in Binary Server, you will run away right now because they're huge. So to make kind of a WCPS 101 smooth, I'm going to show you this one. So basically, you have the endpoint, you request the process coverage, and then you just like plug in the query. In this case, we are querying this coverage. So the image is the data cube, 2 meters, so it's temperature at 2 meters above the ground. And we want it for latitude, longitude 35, so latitude 3565, and then longitude 3580, so that's a square. And we want a period of time. And we want it as a CSV. So this, when you just like press enter, and within approximately like 2 seconds, you'll get like a CSV with the temperature. So we have, as I said before, we have 3 different ways to access the data. And the most complete is the web client. You can access by going to mars.binary-server.view. If you do it now, it will not work because the Wi-Fi connection here blocks 2 of the ports that we use. So you'll see a very nice black screen. But it looks like that officially. So when you enter into web client, it will automatically load the TRDR crisp data. You have 3 main sections. So the center section where you have the globe and all the magic and all the fancy things that are happening in there. The main menu and well, okay. So here you have 3 nice buttons actually to do spectral analysis, spectral ratio, and to change the histogram. So when you open the left-hand menu, the main menu, you can choose different projections. Now we have 3D views, but you have a rectangular projection, south polar, north polar, mnemonic, and the stereographic projection. Base maps, that one is Viking, but we have, if I'm not wrong, a Color, Mola that we use from USGS endpoints. You have the available layers you have. So here we have TRDR and MRDR. MRDR, we just plugged it in 1 week ago, and it's not working extremely smooth, but it kind of works. We only have a few now, it's just testing. So what else can you do? You can search by region, by name of the image, and by latitude, longitude. And then when you press the go to button, it will just go there. So this is a crater, if I'm not wrong. This is a Lomonosov crater, I think, or somewhere in Ilfos, I'm not really sure. Anyway, so I have all the footprints of that reason. So when you click them, it will load a false color RGB combination. When you have prism images on top of each other, you can right click in this area, and it will open the context menu, and you can lock which one you want on top. You can download them. You can download the WCPS combination, or you can download the original image. The analysis part, because visualization, everybody does this, but we want to analyze actually the data. In one of those buttons, the one on the top, there's the spectral analysis tool. RGB, you click to analyze of the spectral signal. You can click and use a single pixel, a kernel of 3 by 3 and 5 by 5 and 7 by 7, I think. Range of the chart. We can load spectral analysis, laboratory spectra actually, to put it on top and compare whether this is the material that you're looking for or not. Spectral ratio, so you can choose the numerator and the denominator, and then it will just ratio the signals. And this is one of the features that we lately add. So, I don't know if you've ever heard about these Grism summary products. So we took them from the Viviana paper and we translate them to WCPS into our database. So you can select any of the products that she has published in CAP, basically. So you can choose them, you can choose which title do you want to put them, and then you just press combine, and then it will show the RGB combination of these 3 different products. By default, we load a stretching number, so it's basically 115 plus minus standard deviation, I think, or the other way around. And if you open the histogram menu, you'll see the histogram and you'll see the max mean values. So you can change them because things that are hyperspectral analysis scientists they want to change their limits, their stretching limits, in order to enhance different materials a lot. So you can do it online with Server. We also have MCube data. Not all of them. We don't have polar data yet. We'll have one polar footprint, but it doesn't look really great. So we'll have one. We're studying what's going on. With MCube data, you can do exactly the same thing as you can do with CRISM, but the WCPS RGB combination. So this part here, yet we're working on that. So WebGIS are cool, but what happens if you want to actually go down into the numbers and then into the code? So Jupyter notebooks are kind of a hype since a few years ago, and everybody does this Jupyter notebook. So we said, like, okay, so we want to have one. So basically, we provide 3 scripts. 2 are Python notebooks, and the other one is just a script that does digital info for one of the images, the CRISM images. It stores that into a metadata.txt file. And when you open the first IPython notebook, it will basically it will read through these metadata, and it will create a table containing band name and wavelength. So it's a relation between band name and wavelength. And we will use that later on. So when you load the Python client server notebook, basically what you have, I have 5 minutes. Okay. That means you have a list 4 lines of code, basically. So you have to set the RGB combination you want with the product, the coverage ID, and then just launch the actual magic. So it will pop an image, which is not a stretch, because we didn't manage yet to do it on the Python notebook, but we're working on it. With the RGB combination you selected, which is exactly the same what we were doing on the WebGIS client. And then by clicking here, it will load spectral segment. Okay, so what would happen if what you really want is to, all these fancy things that we do, you want to put them in your pipeline. So you have cool pipeline, Python pipeline, these piece of coding there. So we did a Python package. It works exactly the same as the Python notebook because it's basically a translation. And you just create a small configuration file, just like that, just a few lines of code. It will ask for the name of the table. So that's the table that we created before. We call it CRISM in this case. And it will just like pop the RGB combination, and then by clicking, it will open different plot script menus, and you will have the spectral signal. So here with the Python notebook and with the loads out of the box the laboratory spectrum, but it's easy to do. If you have them, you just need to pull them, and that's it. So the future. We're testing the tool with MCube data. We've been doing that for the last few months, but it's not working as smooth as with the CRISM. We want to add more data, more body data, series, and Vesta. We want to create a Qt interface for the Python package because that was one of the requirements of. And then we want to add the dynamic stretching to the Python package and to the Jupyter notebooks. So conclusions. Client server. I think it's a reliable open source tool, open source, that's very important. To visualize and analyze, that's also very important. cruising data and MQB in the future. It's highly modular, so you can just like go to GitHub, download it, and change as much as you want. And probably you will make it better. You can add it to existing pipelines, which is one of the requirements of most of the users that we have. And yeah, please, as I said, like go to GitHub and download it, open issues if you want, if you see something wrong in there, use it. And that's what I have. Thank you.
Questions? So why, I have one. So why does Client Server focus so much on the hyperspectral? Is there a reason for that, or?
Because we found that there's not many services doing that. So you have a lot of services that provide you visualization of images. But if you want to analyze CRISP especially, you have to go through Mr. NP and NCAD, which are fantastic, don't get me wrong. But we're kind of open source applicant. So we wanted to provide the community with an open source tool. We have to use anyway SCAD. And but I heard yesterday that they're planning to do an open CAD. So that'd be great.
So are you planning to extend Client Server to other multispectral data sets beyond?
So MCube is now there. I think at Guya we have some plans. We also plan to put just like simple topographic data, like small DDMs from high-rise, for example. Problem is that we're just like two guys. So.
Yeah. Thank you very much. Scott? You're not Scott.
I'm not Scott. How's that? They can hear you? Okay. Sir? This is also going to be the slides.
You should. Slides up. All right, so this is Paul Wren, not Scott Dickenshine. He's going to talk to us about JMARS.
Yes, so I'm Paul Wren. I'm the newest member of the JMARS development team. I've only been there for 3 years. We have quite a few developers work full-time on this product. Pretty familiar with it. And it's been around for a very long time, and it's going to be around for a long time too. We get a lot of support from us, but we're also involved even right now in the early stages of multiple missions that are in the planning stages, such as the Europa mission, Psyche, and the Lucy mission to the Trojans. So that's the good news for us on the team. Obviously, we like doing what we do, but it means that JMARS is going to be around for quite some time. Let's see. I'm going to figure this out somehow. Strike two, that's the laser pointer. And I've lost trend, so I don't have my two here.
Right side of the circle.
Oh, okay, gotcha. So, even though I think most of you know a lot about JMARS, I want to remind you of some of the things. It's a free, open source GIS application that runs right on your computer, runs on Mac, Windows, and Linux. And even as powerful as it is with all the tools that are included, the thing that makes it also very powerful is that we have a large room full of servers at ASU where we can serve up a lot of data to you, ready to go, projected, that you can use in the tool. Search once you're actually running the app through a number of different criteria. local time, emission angles, geographic location, actual date, and combine those to find what you're looking for, because that's what we've been talking about a lot, is how do we find data? And JMARS is pretty good at doing that. Also, for all the missions that we actively support and are actively supported by, everything from the PDS already for those missions, but if they're ongoing missions, we have software that automatically goes out and pulls the latest data. So you know that we the latest data from the PDS for those ongoing missions. Of course, it's a GIS application that has a lot of things you expect from a GIS tool: crater counting, custom shape creation. All those things are there. But we also build custom versions of JMARS that are used for mission planning, like for Themis, MRO, LROC. They've been using it for quite a long time. A new mission, we built their planning layer. And for the Dawn mission, we provide analysis support and a custom version for them, so they can use their latest data to get right when it comes down from the spacecraft. And I want to mention this, we do have an extended demonstration today in the Agassiz room at 3:15. So if you want to come check out some of the things that I'm going to talk about, please do come by. I'm happy to demonstrate anything you're interested in. It works. Okay, so I want to get into what's new right now in JMARS. Like I said, the tool's been around. It's a very deep tool, and I've been working mostly on mission planning, so I'm still learning. This presentation was a great way for me to try to learn more about the tool. We currently host about 4,000 global maps. Of course, 3/4 of those are for Mars, because that's really where we started. But we actually have some new products. There were those new CTX regional mosaics that were made for the landing site work are in there. We also have some interesting new material recently for Mercury, where we have, I think we have 8 new topographically based maps. There's blended shaded relief, colorized radii, slope by degrees, that sort of thing. And for Venus, we added those high resolution side looking global mosaics from the Magellan mission. I know it's not new data, but we now have the highest res data available in the tool. For Ceres, we added recently a number of really useful numeric maps and also some secondary products based on DTMs. And for Saturn, we did add icy moons maps. So, like I was saying, JMARS is all about data. We are hosting a lot of information. And there's a lot we aren't hosting still, but for what we do have, been a lot of talk about CRISM. We have 13 million derived CRISM products in the tool ready to go. You can pull those up and do analysis in the tool on them. I'll just let some of those numbers soak in. A lot of data. So, new functionality. Now, this is just a quick summary slide of the new things we've been putting in the tool recently. I'm just going to jump right. So, Charade. We have Charade data in JMARS. You can use it like almost any other stamp layer. You can bring it up, search on the main map for the Charade footprints you're interested in, and then when you go to the main control panel, this is kind of your control center for Charade. You can navigate around on the radar that yellow line that you see is an indicator of where there's also a marker on the main view. So if you move up and down along the track of the radargram, you can see it in this box. The little white box that's around the radargram indicates if you went to the full screen, which I'll show you next. It shows you where the full res view is centered. Sure. And by the way, as a user, you can draw your own horizons in the tool here. And the tool, let's go back. There we go. You can draw your own horizons, do your own analysis, try to identify layers. All of that can be exported to a CSV for offline analysis. There's also a depth plot for the actual radiogram. And then you can go to the full res display. Do that a couple of ways and export the full res as a PNG. Within our shape layer, which has been around for a while, we've added some interesting new functionality. If you've drawn a few shapes, you can now find the intersection of two shapes and create a new shape from that. You can subtract one shape from another, get a resulting what's left. You can merge two shapes, three shapes, four shapes into a single new shape, and you can also make copies. Another new feature we just added is pixel export. So if you've drawn a shape and you have a sampling source you want to use, you can export a CSV file with every individual pixel that falls underneath your shape and the associated value from whatever sampling source you choose. Coming up in the very next release of JMARS, you'll be able to select multiple sampling sources, and then your export will include a column for each of the sample sources for the value for each pixel. We've integrated now fully the 3D body view into JMARS. So this is a kind of an accessory screen you can open up contents of the main screen onto a shape model. If it's a planet or a very large moon that's essentially spherical, we just use a unit shape model. Useful to do anything beyond. Certainly a global shape model for Mars. If it's a smaller body, and we have a shape model, so we have one for Vesta, Phobos, Ikawa, there's several others, quite a few more. Then we actually lay the material right onto that, right onto that shape model. And you can just, we have a way to export that view. You could just do a screen grab, but we also have a way to export that as a file you could use to include in a paper poster. It's not all that exciting of a feature, but JMARS now supports being used behind a firewall. So if your institution has a firewall, that makes it difficult for you to get to the JMARS servers to get the data you're looking for. So we now have a capability that you can configure pretty easily to use it behind a firewall. Really, really cool thing. We've added several human exploration layers. So this gives you tools to look at or to go look for potential human landing sites. Provide a lot of data for you to say, well, what are the areas that are most useful in terms of local resources to use for sustenance or building structures, or is there a lot of water nearby or water ice, obviously. Where are the interesting regions of interest from a science standpoint? And you can then use those to find locations that meet your search criteria. Also made some updates to our 2020 landing site layer. It now has sites that were the candidate sites going into the last workshop. They're down to 3 sites now, but those 8 are still in there. You can go and see a lot of information about them, examine the area, and we've also basically set it up so you can directly move the map right to the landing sites from the list, so you don't have to go searching for it. Our 3D layer has been around for a while. We've been making some changes, improving the user interface. It basically lets you take what's on the main screen and project it onto an exaggerated terrain. But it doesn't have to be terrain. You can use any data source. So for example, the top picture there shows an actual MOLA elevation with a certain area. You can move this thing around, turn it upside down, spin it around. The second one is actually based on tests olivine abundance. So if you wanted to get a 3D graph of numeric data, where it occurs on the surface, that's a way you can do it. And, oh, I didn't get it out. But cool new thing that we have in beta, it'll be in the next JMARS official release. 3D window, like I've got a window down there showing Gale Crater, you can export that as an STL file and go print it on your 3D printer. Our test layer's been around for a long time. We do quite a bit of analysis here. The thing that I was trying to highlight here is that you can actually take the test information for particular footprints you're interested in, export it as a CSV, and then use that CSV to create a shape layer. It includes shapes that match up to the specific test footprints you're interested in. Then you can do other analyses in terms that you can do, on our shape layer. Now, we've had test data for a long time, but probably by the end of the summer, we expect to have a new revamped test stamp layer that will work just like all our other stamp layers, be very fast and much more user-friendly than what we have in the current test layer. As I said, JMARS has been used for mission planning for quite a long time, but it's very different to actually do mission planning for a small body than it is for something that's always in orbit around the planet. And for the OSIRIS-REx mission, we built an all-new 3D visualization display to show where the planned observations are actually going to occur on the body. So the top image you see there, that's Venu, the shape model, and we use Spice. We have yet another Spice wrapper. This was in Java. We combine that with the targets we compute during the planning creation, and then we can actually display where the footprints will land on the 3D body. And that's a 3D view that you can spin around, look at, zoom out, zoom in. So that's been a really fun thing to build. It's very, very useful to the planners who are creating plans for all the different phases of the OSIRIS-REx mission as they get to Venu. Now we took that capability and are now using it for other future missions to build demonstrations that scientists can use to show what they're planning to do well in advance. And we're anticipating will actually help build some of the planning layers for those systems. The far one, that's Europa. ASU is building the EMIS instrument that will be under the Europa mission. So we put together some actual movies. That's just a screenshot, but some movies showing where the very fast flybys, the footprints will occur. And the other one is another mission we've been working on with a thermal instrument for doing observations of Mars. So instead of opening up for questions, which we can do, I really want to say that we have questions for you. We have a team of people who are always adding new features, but we want to add the right features. And one that we're looking at right now is how to view this for various bodies. And not entirely off body necessarily, but in particular, images that include limb. So we'd be interested in having discussions offline or email us, but what would be the most useful way for you as a user to see those images that show the limb of a body? And Cassini, boy, we've certainly learned this week that there's an awful lot of great Cassini data. We've been funded specifically for Cassini. We do support some Cassini data in JMARS, and we'd like to host more. And we do tend, when we have some free time and we have a particular personal interest or a user who's very interested in some data, we will add in new maps. To look at, in our spare time, adding some more Cassini data, but we're kind of looking to you, the community, to say, hey, this is the top priority, this is the stuff I'd like to see first. So that's another thing. You can send us an email, you can talk to us. We'd really like to know what's the right first sets of Cassini data that we could start using. And in general, what data sets do we not have that you'd like to see? We'll put them on the queue and we'll get them in there as time. So where to get more information about JMARS? We have a website. You should go there. That's where you can actually create a JMARS account if you don't have it already. You don't have to have one. You can log in anonymously or as a guest, use almost all the features. But for example, our custom map upload capability, where you take your own maps you've created or that you have or that we don't currently host, and you can upload them to the tool on our servers, and they're always there for you to use when you log back in. But you can download the installers. We have a whole bunch of great tutorials, both written and video. Some nice videos to explain step-by-step how to do things. We have forums there to contribute, see what other people are talking about. And, you know, we really want you to interact with us. We want you to ask questions if you have them. We want you to suggest new features if you like them. Of course, we want you to report problems if you have them. There's a report a bug right inside the tool, but you can also send help to help@jmars.asu.edu. We've started to join the later 20th century, getting into social media at least, and we now have a Twitter account, so you can kind of keep track of new things that are available. And I don't know if I mentioned this, but we're having a demo, 3:15 today, so come by, see what JMARS does that you didn't know it did. Ask your questions. I've been on way ahead. Anyway, that's it. That's all I have.
Paul, any questions for Paul? Great.
JMARS is a phenomenal capability, and please keep doing what you guys do. I have a question about the customer base. Is JMARS and the interface and the capability easy enough to get into that you have customers that are basically citizen scientists?
Well, JMARS has been used for over a decade in our Mars Ed program. Middle school, high school students across the country using JMARS for the first time to do they actually, if you're in the program, they conceive of a simple science question they want to answer, JMARS to actually do it. So I think even though there's always need for improvement on the user interface in terms of intuitiveness, I have my own issues with some of it. Yeah, I think it can.
So you really don't need a JMARS Lite? This is a question that came up in discussion with Michael Meyer from NASA headquarters. How to get more people beyond people in this room in the science community, that is the citizen scientists, involved in looking at planetary data from the PDS and otherwise.
Sure. I think JMARS could be that tool for sure. Here we go. This is not on Mars 19.
We are embarking on and we are continually improving the user interface, so making it simpler. We've gone through one revision of pulling some features out that were buried in, and we are going through that process even now. So we are looking into how to improve the user interface so it becomes easier to use for the first-time users, and then have advanced capabilities still in there. But it is toggleable functionality that an advanced user can go into a menu and say, show me advanced stuff, or don't show me advanced stuff. On our mind, the first iteration that we did, we reduced the options or the layers that are available for a basic user versus an advanced user. So in the main JMARS layer interface, there's an advanced checkbox. If you click on the advanced checkbox, it gives you much more data. More layers are available to you, more capability is given to you. But we are working on continually updating that capability.
Excellent. Keep doing what you guys are doing.
Thank you.
Yeah, hi. I had a quick question. You had mentioned JMARS allows the ability to create 3D models that are useful for 3D printing. I was just wondering whether that capability was for a subset of the data that you provide, or is it possible is that kind of transformation possible with all data?
Sure, no, good question. our 3D layer doesn't know what data is being displayed in it. So whatever data you choose to use to represent a texture, whether it's elevation data, whether it's other numeric information that's geolocated in the region you're looking at, that will be what you export. It's whatever gets put in the 3D window, you can print. So there's no limitation per se to what data you can represent. And no limit what body you're on.
So I have the complete opposite question to Ray. Of course, this is my my yearly plug to JMARS is you guys continually add export options for images. Still see that geotiff export option. So that's my plug. I think I get a laser every year for asking.
I have one for you now.
Yeah, good. I probably have. I think I said I have 5. Let me see. So the complete opposite of that is we saw a presentation, the Rastaman engine on Planet Server is looking at, it has an interface, and you guys are doing a great job with the interface, but you have this ginormous infrastructure thing in the back end that we've been talking about. Have you guys thought about opening up that idea to the WCPS idea, to make it callable through Python notebooks, to make it callable for command line, the interface, so that data scientists can hit that amazing wealth of data, but not necessarily through the GUI?
Sure, we've been discussing that even here over the last few days as a capability. I have my own opinions, but I think you should address this.
There are some technical challenges that we have to go through to make it available for a wider audience. So that has not really been a focus just because of how various funding resources come in. It requires more servers and more capabilities in the back end, but if there's a need to do so, we can look into that. So the stamp and map infrastructure, given that we host data not just for public use, but also for mission uses, so it has to be work that's needed to separate that out even more, so that our front-facing or public-facing services, there is no possibility that you can go into other areas or whatnot, just through a backdoor or some possibility. As far as your geotiff question, the JMARS uses oblique cylindrical projection. Unfortunately, that's not supported in. That's not an excuse. I understand. So we've been looking at the progression in GeoTools, and that's one of the capability libraries that we leverage on. And upon the last check that I did, they had not added ground control point phase geotiff output. So either one of these days, one of us just sits down and starts coding that capability, or we have to come up with a different mechanism. One possibility is to export data into ISIS-3 files, because ISIS-3 does support oblique cylindrical projection. We have tried that once, and if you try to process it or transform it through GDAL, issues appear because you start getting holes. There are optimizations that are added in GDAL and all the geospatial tools. Hey, you want to query this data, this envelope, into the source envelope. And when you do that around the pole region, you miss data. And that leaves a large donut hole somewhere on the output end. So there are a few technical challenges that we have to get through. Hopefully, we won't have to give you many more of these laser pointers. If there is a backlog, the NASA will catch up to that. If you're giving too many laser pointers to track. But we are working on that.
I bottom line is keep up the good work.
Thank you. And at the demo, come by and take a close look at the 3D print we did of, greater line. Way that you were, so.
Thank you very much, Paul. Thank you for your attention this morning. Let's take a 15-minute break, and we'll get back in here at 10:15. See you then.
So I would say by the end of the year, it will be your budget's controlled. Yeah, okay. Team is controlled by them. Okay. And so I talked to about the way that we're done with control. It will become, yeah, it'll become a version. It'll be real efficient. It's scary. No. Well, and I think the way that we justify it is, so if you made a you expose one layer to don't sweat.
I think what we should do, one, is to go out to the services you provide, expose it to your users, you know how to log into JMARS, now they have extra functionality. You didn't have to exactly right. But don't re-implement. But don't look at their interface. Look at their. It's interesting. It's an interesting concept. Because now it's just regular. I mean. I can stay on my team. I wish you and you can go sure that you can see that. I suggest what the first name.
I think this is where it's like.
The odds in you can see that first time but let's take thank you.
I don't think I'm. No, no, you're not. I'm like third, or I think you're 11:15. Yeah, okay. That's perfect.
Yeah, I don't know what time.
Yes. Finish. Stand two people behind each other.
It's incredibly tedious going through no, I think it's but not really. Really, I haven't explored journalists for that's the sort of thing where and then I get to the point So someone okay. And because my English is pretty high, then you got, well, why didn't you get my Turkey. That's it. I think there's just- why somebody who's in the radar team. So it would be nice to have the 3D printing. So take a look at that. It's not that big. Oh. Yeah, I'm sorry, I've got to go into the church to stand up. Oh, yeah, scientific. I think it's not. If I can. Yes, yes, and I sit down. Take the AGV. I was telling Paul, all it's like. With something specific, like you're looking at the what is
Sorry about interrupting. I thought you were calling out to me or something.
Oh,
Go ahead.
when I'm on the phone, I can't really type.
Okay, oh, you can catch it.
You have to start to-
Except for people who don't know, think you are.
They might be right in both cases.
It was, yeah, it was funny, I remember the first time that Bluetooth, came about, and you had no idea what it was. And I'd see it the first time I saw someone walking down the street, and then I could have.
Yeah, although it's really first three people to have the knowledge, so it's a little bit more obvious.
That's nice feedback.
Yeah, you got shot in the sound. Sound goes directly. Next to an induction coil.
Oh, really?
Yeah.
Now, is there, I've seen a lot of talk, your outgoing speech It's amazing.
Your analysis. Yeah, so at what point does it start actually implanting some bits in their body?
Wow.
Wow, probably not too far away.
No, it's not. I don't know if I want that much accent.
Yeah. I'm not sure either. On the other hand, I may not have a choice.
Yeah.
I've already been told if my hearing gets bad enough where I outgrow the consistency days. Yeah.
Okay, so, it's probably, yeah, now it's probably not as much as it's good. Okay. Something to look forward to.
Yeah. The good news, the thing is, the longer I leave it off, the better the attention again.
Well, and that's 100%. You don't want to get it.
5 years ago, when they put the implants in, this was a major surgery. They literally destroyed what little natural hair left. So that when you weren't powered up, you were dead. Now apparently it's outpatient power, and what little natural hearing you have, you're retained, so that when you're powered down, whatever natural hearing you have is still powered.
Exactly.
Maybe I wouldn't get that enough of the saw. Actually, those things are pretty loud, so probably.
They're designed to be your attention field.
And you also have this.
I remember.
This is me, yes. No, I'm the person. It's next time it's kind of like a scene.
So it has and it's not like you're wrong.
No, it's an image.
Okay, all right. So if you have a hand,
All right, break's over. Now we will get into our next section of talks, starting off with Nicholas Monod telling us about Open Planetary Map. And again, you'll get the first bell at 5 minutes to the end of your window, the second bell 2 minutes later, 3 minutes before the end of your window, so people can ask questions. If you're still talking at 1 minute before the end of your window, then I'll get up and come get you.
All right, everyone, can you hear me? Fine. Good morning, everyone. My name is Nicolas Monod. I used to work as a planetary archive scientist for the European Space Agency for. Now I'm an independent consultant. And I have initiated this project along with other friends and colleagues from within the Open Planetary community. And this project is supported by CARTO and Europlanet. So I'm going to tell you a few words about Open Planetary first. Probably many of you know already about or heard of seen stickers of Open Planetary, but still wondering what this is. Basically, it's a loose organization of planetary scientists, scientific programmers, and planetary science enthusiasts who are coming together to discuss and develop solutions to common planetary research and data analysis problems. So basically what we are is a Slack community where you can chat real time, or run your own channel to discuss whatever you want. We also have a GitHub, and we've been running a blog also since September last year. You can have more information on from the website openplanetary.co, and you're all very welcome, and we encourage you to join. We also have Twitter account, so please feel free to get more information and come to see me anytime. Carto, how many of you knows about Carto? You raise your hands. Wow, that's very few. You may check this later. Carto is a powerful online platform and tool to easily visualize and analyze geospatial data. So it's very much Earth-centric, but it can be used for planetary science. And this is what we're going to use for this project. What is Open Planetary Map? So it's a collaborative effort to build the first open planetary mapping and social platform for yourself, planetary scientists, space enthusiasts, educators, and storytellers. There are existing interactive maps out there, complex for non-experts. There are closed systems that do not allow for collaborative learning, social interactions, and reusability of data. So our goal with Open Planetary Map is really to make it easy to create and share location-based knowledge and maps of Mars to start with, and other planets of our solar system. To show you a few examples of maps that we would like to encourage for other people to create, thanks to the Open Planetary Map platform. So this is a beautiful static map from someone who's not a planetary researcher, has no expertise in planetary science, but created this wonderful medieval-looking map of Mars. Second, we have here an interactive map from Esri that allows people to understand a little bit the topography of Mars, fill up the planet with water up to a certain level, and this is simple for people to understand basic concepts. Third, we have this interactive map, which is more of a story map, as we call them, that tells you about the selection process of the ESA ExoMars rover or the landing sites. So yeah, those are three examples that are of maps that are targeted towards the general public. Right? Open Planetary Map, I should say Open Planetary Map is just getting started. Then to you is just what we want to do. Hopefully in a year's time I will come back and show you more. But those are the main three ingredients that we have in mind for our platform. At the bottom, an open dataset repository. On top of that, we have base maps. And on top of it, we have a web interface that is designed or aims to be designed towards engaging the general public with planetary science. So first about sharing places and the concept that we have for this web interface. On the right hand side, you see an interactive map that pretty much looks like what you would see on Google Maps, where people will be able to discover Mars, navigate it, more importantly, add their own content. So we really want to engage the greater number feature by adding places and also commenting, discussing what's going on. So one example that you may think of would be, you can see in the literature so many articles, photos, panoramic tweets all around. Wouldn't it be great if all this could be geolocated on Mars and everybody could add their own? So that's kind of the aim. Also, what we want to do is we want to let people to easily share location on Mars. So this is going to be done through a simple URL link with a unique identifier for every place that's going to be added on Mars. Would be shareable on social media and nicely rendered. And on the left-hand side, you can see how it would appear in a typical news feed on Twitter or Facebook on smartphone. Base maps. So those are the second ingredients that you really need if you want to create your own web map already. Those were the ones that have been used for a previous project pilot for this open planetary map project that you can already use. The problem with these maps is that they are all come from one single data set, and they are raster data. And in modern age now we've seen vector rendered map popping up earlier if you use Google Maps. So our aim is to move towards a global vector-based map of Mars. And what we want to do is we want to provide a characteristic and representative view of Mars, enabling users to overlay various types of information, as many as possible. When I say the characteristic and the representative view of Mars, I mean, if you think of anybody looking at a map of Mars or looking at the contour lines of the continent of the Earth, they would immediately identify this image as being the Earth. What we're kind of aiming at is to have the same thing for any other planet. So finding a characteristic and representative view of Mars. This shows you, so this is what we've been working on in the last few weeks in terms of starting to craft this base map. So the difference between the other existing raster-based maps is that this base map first is going to be all vectored, and it's going to be a combination of different data sets. So those are the main three information data sets that we have identified so far: the topography, the albedo, and the nomenclature. A region where we have high contrast of relief and albedo to start testing compositing this data set and styling. So for the topography, we are thinking of having some hill shape, contour lines, and right elevation color coding. And see for the albedo, let's see all these spots that will represent the albedo. This is just, we're just scratching the surface, we're just getting started. So this is just to illustrate where we are heading towards. Last, I'd like to tell you a bit more about sharing data sets and this open data set repository. And here, just to show you that all this is going to be possible by using platform. So as I said before, Carto is supporting the project, and that means that we have professional, what we call enterprise accounts, multi-user accounts that can allow us to feed into the Carto database as many data sets as we want, to create maps, style those maps, make all these data programmatically accessible through different APIs. And that means, because Carto typically is a geospatial database in the cloud, Postgres database in the cloud. Lots of geospatial analysis and visualization. So also from this diagram, you see all the different types of users that will be using the open platform. So you have the public users who are gonna use the main web interface. From this interface, you will be able to add, edit places, and this is going to be fed into the Carto database. Here is the OPM team and contributors. This is us, and this is what we're going to be using to let's say to populate the database. Other type of users, it's actually not a user, but it's more of an application, and we really hope that this will encourage the development of third-party applications, which would be 2D interactive maps, 3D virtual environments, games, online course. Yeah. So that's pretty much it. Also, what I could mention here is that from all the data sets that are going to be in the database, we're going to be able to dynamically generate and expose this vector-based map to developers who wants to create their own visualization on top of these base maps. So yeah, that's all I have. It's a very short presentation, but if you're interested, we really want to make this useful to you because we think that also we can bridge between the researcher community and the general public. So if you want to have more info, just go to openplanetary-map.org. You have much more information on our GitHub repository, and you can follow us on Twitter. Thank you for your attention.
Since we took a little bit longer break, we'll
Oh,
go ahead
we got
and
one.
move on to-
We got one.
One more, okay, one, yes.
This on? Yeah. Hi, I'm Alex DeWolf from Labs with the University of Colorado. I was wondering if you are thinking about displaying orbiters like, say, MAVEN, or ground tracks, magnetic field data, atmospheric data as an overlay on this.
Yeah, absolutely. We would like to dynamic temporal data as possible. So it would be things as simple as also as the sun terminator or spacecraft where ground tracks.
Well, come talk to us. We would love to be involved.
Yeah, okay.
Can I make one comment? So, okay, so we talk about all the spatial infrastructure. We keep on, as USGS, we keep on trying to pull out this term cartography from our workflow. And I'm excited for this project because now we can talk about the data, and now we can get back to let's make it cartographically pretty. So I'm excited for this project.
And I always thought that cartography meant more than other people did. I always liked that term, so I don't know why you're trying to yank it out of it. All right, so next up, we have Ryan Anderson. He's going to be talking to us about PySat, the Python Spectral Analysis Tool.
Okay, it's working. Can you hear me? Yes?
A little louder.
A little louder? Okay. So today I'm not going to talk about mapping. I'm going to do a little change of pace here and talk about a Python tool that we've been developing in point spectrum. And so a little bit about the motivation. So spectral data are really powerful data, as you all know, but you also probably all know that they usually require some pretty specialized knowledge. Data is released. A lot of people just don't know how to use it, or I can vouch even within a team, not everyone knows all the details of the calibration pipeline and all the steps that are being applied to the data to go from the raw data to the result that scientists are using. And so deriving meaningful values is not trivial. Things like mineral abundance or chemical composition that you get from a spectrum. It takes a lot of massaging of the data to get to that, and it takes a lot of pre-processing, and then there are all sorts of interesting advanced methods like machine learning out there that scientists may have heard of, but not know how to use, or may just never have even considered trying for their data. And then finally, tools are not always shared or easy to use, so lots and lots of people reinvent the wheel for these sorts of things. Also, there's a lot of data to work with. I'm on the ChemCam team, so my personal interest in this is that ChemCam has more than 400,000 live spectra from Mars. APXS on the Curiosity rover has far fewer because it's a contact instrument, but as the mission continues, they're accumulating hundreds and hundreds of spectra as well. 20 SuperCam, sort of the next generation ChemCam, is going to have similar data output, but it's also going to have Raman spectra and V-near spectra. We're just going to be Brownian spectra. And then the Pixel instrument is a APXS-like instrument that'll do sort of maps of rocks, and that'll collect a bunch of spectra. MER, just by virtue of its longevity, has tons of spectra from some of its instruments. And then, of course, orbital data produces tons of spectra. The stuff we're talking about today, we're not locating spectra on a surface, but there's no reason you couldn't apply these methods to orbital data if you want to. So given all that, we need a tool to allow users to experiment with data. It's nice and flexible and powerful, but you don't have to sit down and write a bunch of code and reinvent the wheel. So we were trying to create something that's free, open source, uses existing libraries, so you're not reinventing the wheel, has a graphical interface, so non-programmers can use it and get something useful out of it, but is flexible and powerful enough to do all the different things you might want to do, play around with the data pipeline, things like that. So our hope is that PyStat starts to address some of these needs. There's sort of two paths that are being pursued under the umbrella name of PyStat. One, which there's a poster on this week with Lisa and Jay, they're leading the side that's trying to place spectra on a surface, so orbital data. And so they're just spinning up that effort right now. The point spectra stuff that I'm talking about today, we've been working on for a year and a half or so, and we're going to be continuing on that under a PDW project. So the focus so far with this point spectra tool has been, just because of my expertise, chem type data processing, the types of things that we like to do to our data, or that we would like to do to our data. But the tool doesn't care where the data came from. It's just reading comma separated value files, so completely transferable to other data sets as long as you get them into a simple CSV format. Before I go much further, I'll talk a little bit about multivariate regression, just so that the jargon is out in front. This has been sort of the focus of the tour. This is what we do with ChemCam to go from spectrum to composition. So the idea is you're taking a whole bunch of variables, your spectrum, you're trying to determine a single variable or a small number of variables, the composition of the rock. It tends to perform better than a lot of simpler methods because it's using data from the whole spectrum rather than some isolated feature that a human picked out. Type of supervised learning. So you have a bunch of training data where you know the answer. You have the spectrum and the composition. And that's what you build your model on to then feed the unknown spectra to get the composition form. And then just some terminology that I'll probably use. Training set is, like I just said, you have a bunch of known examples for your model to learn on. Test set is when you take some known samples and set those aside. You don't let the model see that until it's been finalized, and that gives you a more reliable estimate of how your model is doing. Overtraining is just training your model so much that it can't handle new data. I liken it to, you're doing a polynomial fit to noisy data, and you use a 100-degree polynomial. You'll fit that data really well, but if you give it new data, it's not going to fall in line. And then folds is when you're trying to avoid overfitting. You tend to split the data up into folds, which are equally sized chunks of data, train a model on the rest, and iterate over it in the process of cross-validation. And it's a way to choose the parameters of your model. So with those in mind, let's take a look at what PyStat actually is. We designed it with a sort of a modular interface, so you add the steps that you're going to do to your data in workflow. And it works, as I mentioned, with CSV files. They're very simple format. They're read in to a pandas data frame that is then manipulated through all these steps. We have a utility in the tool that reads ChemCam data from the clean calibrated spectra format. We're working on something that will read the raw EDR format that's not supported yet, but it's coming soon. And then, yeah, the idea is it's a flexible tool. You can assemble these sort of modular workflows in whatever order you want, to the extent that it makes sense. Like you can't do stuff to data until you loaded data, but it gives you as much freedom as you could possibly want for the workflow. So once you come up with a whole bunch of steps that you want to do to your data, you don't want to then have to manually re-enter those every time. So we've been working on a way to save that and then bring it back so that all your work is restorable, and you can send that to someone else and they can do the same thing. So the steps are sort of organized into a few categories. First is pre-processing. We have a bunch of basic capabilities, things like interpolation. If you load two data sets that have slightly different wavelength bins, you can interpolate one onto the other. If you have areas of the spectrum that you want to ignore for some reason, either they're bad data or you just don't want to see the lithium line for some reason, you can mask it out. Normalization is something we do a lot with libs data, where you may shoot the same rock twice. One time, for whatever reason, some subtle physical change, the spectrum is brighter, but otherwise looks the same. If you normalize it, you get rid of some of the variations. Multiplication by a vector, for example, if you have an instrument response that you want to apply with spectra, you can do that pretty simply. And then, as I mentioned, you can divide it into training and test sets to then proceed through your regression. And we have a handy tool that splits things up into stratified folds, which means it sorts the folds based on the sort of characteristic you're trying to predict with your model, so that each fold has sort of the same distribution of that variable, so that your cross-validation is more effective. And then advanced capabilities, and I'll go a little more into detail on these ones in separate slides, but we have a bunch of continuum removal options and dimensionality reduction like PCA and ICA. And coming soon, we'll have denoising and calibration transfer, where you take spectra from one instrument and transform it to look like spectra collected under different conditions or on a different instrument. So here's an example of continuum removal. I'm not going to go through all these algorithms. A colleague of mine provided a bunch of ready-made code that we just incorporated here. So you could remove continuum to your heart's content. We do have the wavelet transform that the ChemCam team uses implemented, and you compare that with all the other different methods. Lab spectrum with, you can see the blue line and the bright green line are two different continuum removal methods applied to that spectrum. And we have dimensionality reduction. So if you just want to visualize your data on a 2D scatter plot, you can do a principal component or ICA transformation. And then we have a handy utility that makes pretty plots. This plot here on the left is showing the first two of the ChemCam training data set, and it's been color coded because in this case we do know the composition of these points, the magnesium composition. So you can see a little cluster of high magnesium polyamine targets that we have in our data set. And then on the right are the loadings that are involved in producing those scores. Stratified folds, as I mentioned, this is when you split up the data, and the histograms here are just showing you of interest and then assign iteratively to each of your folds. You end up with, not identical because the data set is not distributed perfectly identically, but you get pretty similar folds, so that when you're testing, your test set and your training set have similar distributions of all the variables. Once you have folds, you can do cross-validation. You can hold out the data, iterate over it, and in this case, this is a partially squares model. This is what we use for ChemCam. Check out how many components should I use for my model, and you look at a plot like this, and you can see where the green line and the red line diverge, basically where you stop getting a benefit by making a more complex model. So you choose about 6 components. And then regression. We're leveraging very heavily the scikit-learn Python library for the regression algorithms and some of the other algorithms. We basically just have to write the graphical interface to the regression methods that are included in that library. Right now we have ordinary least squares, partial least squares, Gaussian process regression, orthogonal matching pursuit, and lasso implemented. There's a ton more in scikit, and it's not that much work to add them. So soon we will have all these other ones. I don't know what all these do, but they're things that are available that we can try. We can see if they work for our data, and if there are other methods outside of scikit, we can of course add those as well. And then we also implement submodel regression. This is a technique I developed with the latest ChemCam calibration, where instead of expecting a single model to all different potential types of rocks you could ever see, it's beneficial to actually train models on restricted ranges and then blend them together into some sort of final blended model. So this is just showing on the left, we have 3 submodels for silica, a sort of low composition, medium silica composition, high composition models. And if you blend them together, you end up with slightly better predictions than what you would get from a model just trained on 0 to 100%. So the tool can do that as well. So that gives you an idea of what the tool can do. Of course, there's plenty more that we want to do. We're actively developing. First thing is just streamlining the code and the interface so that someone other than me and my students can look at it and use it. But we also want to do simple function fitting. You know, if you just want to do a bivariate plot, fit a function to it. Clustering and classification, non-supervised methods and classification. Those are in scikit-learn also, so we just need to, again, access those methods. Improving PCA and ICA, so you can project new data onto an existing projection, things like that. Outlier removal, calibration transfer. And then applications, of course, you know, we want to use this for stuff. I'm a scientist and a programmer, so I want to use this to help us improve the ChemCam calibration, develop the SuperCam calibration, and I want to throw other data sets at this. We haven't tried this yet, but there's no reason you couldn't throw other data at it. And this provides access to all these different methods that you can apply to that data. So if this is something that you're interested in, if you want to check it out, here's a link to our two GitHub repositories. One is for sort of the back-end code, which is just PySat, and the other is for the graphical interface for the point vector tool. So check it out, give it a try, see if it breaks, let me know if it breaks. And with that, I'm happy to take any questions.
Questions for Ryan?
Hi, Carrie Wagstad from the Jet Propulsion Laboratory. I worked with Nina Lanza on analyzing ChemCam data specifically for detecting interesting anomalies, scientific anomalies within the data, or novelty detection, however you want to think of it. Are you interested in expanding beyond scikit-learn to use other methods as well as provide those as options to the people using PySat? Because I'm happy to point you to this other capability as well that already works with ChemCam data.
Yeah, absolutely. I'm just using scikit because it's easy. So,
yeah, okay, so do you envision this as being like, let's put everything we can possibly out there?
Yeah, throw the whole kitchen sink in there. And
yeah.
Let people have access to that instead of having to write their own code.
Yeah, right. Okay.
The idea.
Thanks.
All right, thank you, Ryan. Please pass off your lavalier mic. All right, and Mark Hunter will be talking about the Planetary Geologic Mapping Python Toolbox. All right.
All right, good morning, everybody. My name is Mark Hunter, and again, so I'm still a fairly new face in this community, and I've been working with at USGS for a little more than 2 years now. And as a resident GIS Bubba, what I've been doing has been expanding a bit over the last couple of years to meet a lot of the community demand because, you know, in the context of the planetary spatial data infrastructure and all the things that we talk about between, you know, how the sausage is made between getting, you know, pixels in the right place to then getting the right capabilities in the hands of the users that need to use these tools and leverage the data that's being generated. What I really love about this is not that it's so impressive, but because it's so useful. And so hopefully as I go through this, what you take away is that there are a number of solutions that are coming up now that should make life a bit easier for folks that do what they need to do and support the decision-making that's happening so that it doesn't remove the onus from researchers on understanding how their data are manipulated, but allows, reduces the barriers to access those data they want. And I'm actually going to start this off with a throwaway slide that I didn't even expect to retain, but brought it back after some of the other talks that I've seen this week, because this really does seem to typify a lot of the conflict that we see in the differing opinions of where do we draw the line between providing tools and access protocols, and then again, but then still understanding what's happening without you know, totally giving into the black box. Because especially, you know, as a resident ArcMap apologist on campus, I get that all the time, and I totally understand it. But at the same time, it would be kind of silly to ignore all the capability that's here and the robust functionality that they continue to add to. So again, good thing I didn't have to make this toolbar, but I'm sure you've seen, if you have ArcMap users in your organizations, they probably have a project that looks like this. Because every time you put it, Esri puts out a new version of ArcMap, toolbar. And then everybody gets to create their own now with every plugins that are easy to author. And you're pretty soon, you're spoiled for choice. And with all of these amazing options, there's very little direction to these tools and what is the best fit for your use case. And that's really ultimately what this keeps coming back to, and I'm glad that I've been hearing echoed throughout all these talks, is that these need to be founded in a use case that continues to serve as an honesty check for these tools that we're developing. And so again, so the role of GIS tools, at least as I see it, is to again reduce those barriers of entry for researchers to access and manipulate spatial data, and especially as we move beyond strictly geospatial data into spatial temporal and hyperspectral data, these all still again just need to work, and that's still what is at the root of what people talk about with this spatial data infrastructure, is that it needs to just work. And it should really support decision making, produce reproducible spatial analyses. Now, I remember on day one, when Ross mentioned that we should be removing the requirement for researchers to be spatial data experts. You know, I will kind of take issue with that as a geographer. And as I continue to crunch over the last couple of days, the really thing that sticks with me is that it's true. We need to put a cap on that. Again, people need to understand what's happening computationally to their data, mathematically and geographically, that impacts the results that they're working with. The approach I've taken to this, and again, something that I think will make this more applicable to some of your other institutions, are creating tools for general use, and taking very specific tools and expanding them in their flexibility to be more applicable to the greater community. Because then when people are able to see the relevance and importance of these tools, I think we'll start to see them shared more openly and collaborate to continue to bring them up to speed and make sure that they're doing what we need them to do. And so, and really, a lot of what I'm going to be doing here again is, none of this is anything that can't be done on its own, but it really makes life a lot easier. The people that I work with and I work for, a lot of times you say, at the end of the day, you go, I get paid too much money to spend 2 weeks collating a whole bunch of tables or running over and over again, because there's nothing really special about that task. However, as the PI or the person responsible for it, they have to have their hands on it. And so, this is a great way to kind of delegate the work without delegating the responsibility and onus of the product. So, automating common spatial data management tasks, and then also assisting mappers with identifying errors in a GIS. So, even folks that have been mapping in a GIS or working with that for years often don't understand fully what these errors are, other than if I build a topology and I validate that topology and it spits out a bunch of dirty areas, well, I guess I need to go fix them. But as with most GIS applications, and especially, there's always more than one way to do that, and there's very little consensus on the best way to do that. And so, again, these tools should be ways that help mappers take control of their information, and so that as they continue to modify it and to answer the questions that they need to answer, science, that they can stand behind those results because they understand exactly what's going to happen. And again, ultimately what I'm getting at here is that these are ultimately looking at data exploration tools and not canned data solutions. Things, again, the expanded functionality within ArcMap in particular, you can get an answer to just about any spatial problem that you have. That really doesn't mean it's the right answer. And again, where things can kind of fall short of what you would ultimately want, the solution that you're getting, because you got one, there's not a lot of ancillary information as to how those computations, what was happening to And so what I'm, again, trying to back off a little bit here is to just enable researchers to explore their data and understand what it is their issues are, understand what their issues are. And now a lot of people think of capability and functionality as being nearly synonymous. And that's, again, why I really like this subject, because this is kind of where the rubber meets the road. And we need to use this not just to say, hey, here's a whole bunch of, because if this was just about, hey, this is the Python toolbox that we made, and this is what it does, then this would have been a talk for the Mappers meeting the last couple of days. I've here to expand the topic because we need to be able to more clearly delineate between capability and functionality. Just because we can do something doesn't mean it's always what we should be doing. And understanding what those caveats are and how to, one, draw that distinction, and then two, put those in make those distinctions readily available to users is where these tools come in and can be very valuable. So obviously the ArcPy library and the ability to script within ArcGIS is nothing new, and it's great. It allows people to access a lot of geoprocessing tools and chain their workflows together to automate things that normally do take quite extended periods of time. And because of minimal development, more and more people are able to do this for themselves. And more important is that they understand what's going on. And then, and over the last year, especially over the last decade, people have been coming up with excellent models for their use cases, especially things like Model Builder that just allow you to drag and drop in these tools and point your data and say, okay, take this input, process it, then hand it over to the next tool, process that, and then you've got your end result. They're fabulous, and I think it's a great way to get people involved in a GIS for their specific uses without having to farm out cost for development. But a lot of times these models lack flexibility to handle different workspaces and environments in different data formats because you made it for your own use. But it only works on a shapefile, or it has to be in a feature data set in a geodatabase with a common spatial reference. And at that point, that's where you lose about 80% of your intermittent users, is that. And so I'm actually really not going to spend a whole lot of time on the actual tools themselves because I'm going to be demoing those later today. Again, they are what they are, and you can come check them out for yourself. But the best thing about what we have with the Python toolbox, it does this in a very easy, nice, containerized fashion that allows you to share your toolbox with other people. It supports tool environment settings, even additional licensing and documentation that you want to use from the App Catalog video or window from really any location. And so, and as long as you're, now the asterisk that goes with this is when you're creating these tools, you need to understand that what your typical Arc user is going to have installed on their machine. They typically don't have custom configurations of the libraries that they have. So ArcGIS Desktop 10.3 ships with, you can see the version of Python, NumPy, and Matplotlib. And so if you want to get around any dependency hangups, you do also need to develop with that in mind. But again, these libraries will, again, 99% of what the average user is looking to automate in the GIS. And you can see the way it's set up is a Python script with associated XML for tool help dialogues and different things like that. It is just this Python template script that it can read in easily and understands how to parameterize your tools with everything that you need to handle different data types that are common to a GIS. And they make it available so that you can just throw your code right into those execute blocks and define your parameter objects, and you're up and running. It really is very simple and very fast. And so just a really very quick top-level view of what some of these tools are. Again, Trent had a script a while back of merging tools because so many people would have different shape files, a whole bunch of shape files, one for every geologic unit instead of one shape file with attributes for each geologic unit. And it just simply does that, and it can search recursively through subdirectories and appends the file name as an attribute. Again, topology check tool creates topology and adds all the rules that are most common, supports line polygon type data. And it applies those topology rules and adds your class and validates it. And that way you're just left looking at the results so that you can go in and fix what needs to be fixed. And again, but one of the things to note here, again, this isn't a substitute for knowledge of what a topology class is in our map. And so it does still require some specialized knowledge. That everyone wanted from the geologic mapping community was to build polygons. You know, going from lines to polygons, and if you have a previous version of units, to carry those attributes forward instead of going through the process of polygons to points and carrying those attributes forward. Again, this puts everything in one click and allows you to continue through your workflow without getting hung up on the in-between. Again, another recent one is the slope aspect tool, very simply extracting underlying, you know, input a DEM, it's either slope or aspect. So if you have been running a 3-point tool, you need to check your results. You can see potentially what impact or influence the ground may have on that. So again, what I really want to do is encourage people to come to the demo that Trent and I are putting on for ArcMap and a bunch of other issues that we're going to address for people at 1:30. And this is where you go to download the GIS tools. We're adding a lot more information there. And please, if you have tools, models, scripts that you've been using that have been very useful in your work, I am just about guaranteed they'll be useful to someone else. So please send them into me, and I'd be more than happy to work with you to see if we can into the next version.
Questions for Mark? All right, and where is that demo this afternoon, Mark?
Agassi. The Agassi room, yes. Okay.
All right, now we have Christian Liddell again, talk to us about crater counting on heavily cratered surfaces.
Okay. Okay, thanks again for the introduction. I'm going to talk about a tool to derive crater size frequency and distribution information from outside the ArcGIS environment with still under construction. So to start with the scientific background, we have an image of the lunar surface here. On the lunar surface, we can distinguish between heavily cratered regions and sparsely cratered regions. And we know that heavily cratered regions have been exposed to impact cratering over a longer time than sparsely cratered regions. We can thereby speak of old surfaces and young surfaces and assign ages such as area A is older than area B and area B is older than area C. Now, in order to get these ages and the stratigraphy into figures, there are 3 steps to conduct in the GIS environment. First step is the digitization, in which we identify research area of interest and impact craters of interest. Second step is the GIS analysis, the application of crater counting techniques. This determine which craters are included in the dating procedure and which reference area is attached to each of the craters. And third part is the statistical analysis, in which we analyze the crater size frequency distribution of our area of interest with crater formation rates. Now, there are 2 tools available to conduct this whole process. One tool is the ArcGIS add-in crater tool, in which one can, let's say, conduct step 1 and 2 in ArcGIS, and the second tool is crater size to conduct the statistical analysis. Okay, during my talk, I want to focus on crater counting applications. Crater counting techniques available. It's 2 of them are well-established techniques: the traditional crater counting and the buffered crater counting. And two of them are new techniques, the non-sparseness correction and the buffered non-sparseness correction, which still have to be implemented in the GIS tool for planetary surface data. All right, let's go on to crater counting approaches. I start with the well-established crater counting techniques, the traditional crater count. And to the left, you see an example for a reference area with square here. There are 5 craters of interest, craters A, B, C, D, and E. And during traditional crater counting, every crater that has its centroid inside the initial reference area is considered for the dating procedure. So in this case, crater number C would be excluded as it has its centroid outside the initial reference area. It remains unchanged during this process, and every crater is equally considered. Okay, to improve statistics, it is possible to apply a buffer to the reference area for each of the craters. And every crater which has its centroid then reference area is considered for dating. In this case, crater number C would be included in the dating procedure. The crater rim intersects the initial reference area, but the centroid is located outside of it. Okay. Now, the idea of the new crater counting approaches is, when we remember, during the statistical analysis, we compare the crater size frequency distribution to crater formation rates. Now, on non-sparsely crater surfaces, what we see in remote sensing data is not necessarily everything that has happened over time. If we look at the image to the left here, we can see there's a large impact crater, but we don't know what the surface looked like before the larger crater hit the surface. So we don't know how many were erased when the large crater hit the surface. So that means we can only be certain about the formation rates of smaller craters outside the influence area of this large crater. Okay? That means that on heavily cratered surfaces, the rate of crater formation may differ from the observed number of craters. In order to consider that, there are 2 new crater counting approaches available. One is the non-sparseness correction. And during non-sparseness correction, again, as in the traditional crater counting, crater number C would be excluded because the centroid is located outside the initial reference area. And for the other craters, for every crater, all the larger craters plus the surrounding buffer are excluded from the reference area. Okay, so that means that the smaller the crater gets, the smaller the reference area gets, and thereby the weight of smaller craters is increased. So to go back to this slide, the idea of the new crater counting approaches is that the number of smaller craters were undercounted with the old crater counting approaches. Crater number E is excluded since it's located on the rim or the projectile blanket of crater number A, so on a resurfaced area, so this crater would be excluded. In order to improve statistics, again, it's possible to apply a buffer to this non-sparseness correction technique, which is the buffered non-sparseness correction. And in that case, crater number C would be included because the centroid is not located intended research area. Crater number E is still excluded because it's still located on a resurface area of crater number A. And this technique is computationally much more intensive than crater counting technique because we have to deal with holes that are generated in the polygon that have to be geodesically buffered again. So, okay. And according to Kneisler, these are the results to expect from the new crater counting technique. So this is a research area on the heavily cratered lunar far side. And when we apply the traditional crater counting, this is the crater size frequency distribution. Now, the dark line here is the lunar production function, which describes the relative formation rate of impact craters on the moon. And we see that there's an offset in the crater size frequency distribution here. So it's not consistent with the production functions, with the rate of crater formation. So if we apply the new technique, we can see that there's an uplift of these smaller crater diameters, and it fits much better to the lunar production function. So my colleague, Chilla August, she had a presentation at LPSC this year where she investigated lunar basins using buffered crater counting and the new crater counting technique. These are the results from buffered crater counting, and she summarized the crater size frequency bins of lunar basins regarding these geologic time periods. So there's Imbrian basins, Nectarian basins, and pre-Nectarian basins. I don't know if it's a bit hard to recognize, but these lines demonstrate the lunar production function for the respective ages. And using buffer crater counting, we can see that there's a mismatch between the and the actual crater size frequency distribution. And it is heavily debated in the science community whether this offset is due to different impactor populations that have hit the lunar surface during the nectarian or pre-nectarian period, or whether this effect is due to geologic effects. And we apply the buffer sparse direction. It seems that this effect is, let's say, that these crater diameter fit better to the lunar production function. So that would be more consistent with a single impactor population or with an impactor population that has the same, let's say, crater size that is responsible for the same crater size frequency distribution. Okay. So, okay, what do we have? To go back to Crater Tools. Crater Tools has tools for the first step, the digitization, and the traditional crater counting and the buffer crater counting approaches implemented. Crater counting techniques are not implemented. Crater Tools is pretty good at what it's doing, so why not implement the new approaches in Crater Tools? So the problem is we observe limitations when it comes to Crater Tools. Crater Tools is based on ARC objects. And these ARC objects are limited to 32-bit and single-core computation. And since these new approaches are computationally much more intensive and it's inefficient to implement them using Crater Tools, so Thomas nicely had a demo version of Crater Tools where he implemented the new crater counting techniques and it took hours to process the shape files, and that's not very efficient. That's why we're creating new tools to support 64-bit and multiple computation. It is based on open libraries, so mainly it's the GDAL environment, in order to efficiently implement these approaches. As a bonus, we are also ending data intersections automatically, and the plan is also to have polar intersections automatically considered. We're working on it. We also have a shapefile output as a bonus. So that has previously been an issue with Crater Tools. On libraries that we can transfer to other server environments or other computing S3 licenses. Okay, but the main reason we're doing this is actually here the low performance, so that's the bonus. Okay, so what needs to be considered for crater counting? Since we use the GDAL environment and OGR measures, let's say, handles data within the projection, need to find ways to implement geodetic distance calculations, geodetic buffering of polygons, treatment of self-intersections of polygons when we buffer them. It's really difficult here when we buffer polygons with holes, and we have to find workarounds to generate proper outlines for holes and for the self-intersections. So, yeah, geodetic area calculations are considered of the data intersection. Polar intersections, we're still working on that. Okay. And we have multicast faults. We have to, the script is generated in a way that it can have multiprocessors according to the number of cores that the user has. Okay, so there's a lot of code, and all these aspects are technical, and I don't want to go into detail in all the technical stuff. But I can tell you how far we are. So it's a lot of code we have at the moment. Implement the buffer crater counting, non-sparseness correction. Data intersections are automatically recognized and handled. Shapefile output supporting the multi-core computation. We're currently working on the buffer non-sparseness correction and the treatment of polar intersections. When we're done with that, we're working on a graphical user interface. Okay, to conclude my talk, the new tool is the influence of crater obliteration on crater size frequency analysis, and the performance gain we already see is mandatory for the efficient implementation of these new crater counting techniques. We're currently working on implementing the buffer non-sparseness correction, the treatment of polar intersections, but after that we're going to implement the graphical user interface. Okay, thanks for your attention. Can I take questions?
It's good to see. I'm excited to see the end result. What I worry about with the graphical user interface. Can you explain on that a little more? Are you planning to use ArcMap or QGIS, or are you going to build your own?
Okay, I'm trying to build my own. So the thing is, sorry. So if we remember the 3 steps, so basically I'm the only one who's doing the coding at the moment. takes a lot of time and I want to get my PhD done and so on. So as a first step, we have these 3 steps, right? At the moment, step 1 and 2 are handled within the ArcGIS environment, and step 3, for step 3, that's a separate tool, which is based on IDL. In the first step, when I'm done with this graphical user interface, we still have the digitization in ArcGIS, probably using the toolbar. Then as a second step to conduct this data analysis, we use the shapefiles in a separate tool, and then we have a third tool to conduct the statistical analysis. So this will be the first stage of development. Future, what we are aiming at, is to have the digitization in any GIS software, ArcGIS, QGIS, data counting and the statistical analysis in one tool, but in the first step it's going to be 3 tools. It's not very handy, but that's the first step. And as I said, I want to get my PhD on this. It's very time consuming.
Okay. I just don't want you to write another GIS.
No, no way.
Okay.
All right, any other questions for Kristen?
Oh, by the way, I just remembered, sorry for interrupting. I've experienced, because I'm working on Windows, and I've experienced that sometimes when I work on multi-core, and I want to, let's say, forward GDAL to a multi-core process, but sometimes GDAL is not, let's say, passed to the process. It's not a problem on Linux, it's just what I experienced with GDAL on Windows. So if anyone has a comment on that, so please approach me. It depends a bit on where in the code I start the multi-core process. I don't know why that is. If anyone has any experience with that, why that could be, so please approach me. Thanks.
GDAL will be under contract, so we can ask him.
Okay. All right, great. Thank you. All right, so next, Fred Califf, once he gets his screen up, there we go. We'll be talking about the multi-mission geographic.
Good. It's approaching midday. Can you hear me fine? All right. Magic happens. So today I'm going to talk about the Multi-Mission Geographic Information System for Science Operations, test case using MSL data. And I want to thank my co-workers in this project, Hallie Gangala-Barca, Tariq Solomon. Hallie worked with localization of science data products. Tariq Solomon was intern for a year, developed a lot of the interface. He did a fantastic job. You're welcome. Parker Abercrombie, who worked with doing some of the ARM localizations, for science engines on the ARM, and Mark Paul helping with kind of doing things on the web and also working things like on the cloud. Okay, so I have a lot of slides, so I'm probably going to go quick, and I'm going to try to do a demo, hopefully closer to the middle than to the end. So a lot of times, so I'm a geologist by training, however, I'm a mapper by technique. And so I'm often crossing the barrier between engineers and scientists. And so when they have a question, they come to me like, where is the rover now? Where have we been? Or science will say, what observations do we have for this location? What instrument? How much of this oxide was found? What science results are down? How many observations do we have? So these are all typical questions people ask during the mission for the MSL rover. How do you answer those questions? Well, usually you make a map, right? So you can make a map saying, oh, what's the high-rise coverage over Gale Crater? I need to see a map. I need to know the elevation contour starting from this point so we can drill every. Where are all the drill holes located? And what are the modeling images for those drill holes look like? Where's the rover today and how does it relate kind of to the spatial context of where are our targets made by Jeff Schroeder, who, by the way, is around here. He's making target maps for himself. Where were the science observations taken and what were they named and what types of observations we have? So these are all maps that we can make, but larger maps for overall geology for publication. So these maps are all great, they're functional, useful, but we get into this problem where maps need constant updating, which means there's this iteration cycle where science team member or engineering has a question, they come to me, I make the map, and I give it back to them, they go, oh, but could you, like, I want to see more to the west, or can you zoom in a bit, or can you add in slope data? Can you just show me only the apex data, not all the targets? So all these questions, you know, we have this iteration cycle, which is slow for team decisions that day or that hour. And so we want to speed up that process. And so we have the bottleneck problem. So few mappers, so many requests. There's a lot of people do mapping on the team, but not everyone. Everyone wants to see things on a map generally. And so we get the iteration cycle, and also some data sets are unique. You know, someone says, oh, I'd like some elevation data. I go, here's a 5 gigabyte DEM. Oh, when I pull it in Photoshop, it's all black. Well, this is very good data, blah, 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 right? We're data scientists, we can handle it. Typical geologist or science member usually does not. So we want to have a way to break that cycle. So what we have now with mission data, current state, you know, we have lots of seismic data that we can, in theory, localize out to millimeter accuracy. However, the bigger component is time. How do we find out where that instrument was pointed? You know, was it from a mast and you have an elevation? Was it on an arm? We do, sometimes months. And so our objective is to develop kind of these tools and interfaces and standards to localize science data products. So we know where on Mars it actually occurred and in relation to other observations on the ground. And so the desired state is this near real-time, daily, solely, that's a word, accessing science data and then provide a way to look at it in a geospatial context, in the mapping interface. So these are the MEMGIS goals, to define these labels that we would push into the science data products and get their localization where they are on Mars, either on their commanded position or based on how they actually were taken at the time on the surface of Mars. So we want to automate this for instruments that are on a variety of platforms and develop, again, this mapping interface to intersect with it. And these align with the multi-mission ground system and services, advanced multi-mission operating system services, MGSS, AMOS. I have to read it because I cannot remember. I always drop one word in the acronym. Who's supporting MMGIS, operation times, costs, and risk, leverage new technologies like open source software, which MMGIS is built on, and then to provide support for future missions. So we get lots of data from orbit for any type of landing mission. And I'm going to, this is a guide towards landing mission, although the software is a little bit more multifunctional than that. Model data from doing a landscape analysis, we get elevation models, slope data, traverse cost maps we make, vector lines of potential traverses. So we want to have these all co-registered, combined, and then we have the data we can get from the rover in so little time. We have at least 12 instruments. Some of them are body fixed, like the MARTI download camera or the REMS instrument, which records wind, temperature, and pressure. They fix the rover, so they're kind of attached to wherever the rover goes. You have things that are pointed, like MassCam or ChemCam, where they have this azimuth, elevation, or range from the rover. Then we have things that are contact science, things that are on an arm, APXS, the MOLLE, our microscopic imager on MSL, or where we drilled on the surface. And so the problem becomes, and then we also have, of course, the data back from the instruments. And the question is, well, there's a spectra, you got a great result. Oh, look, there's a carbon peak. Did all the other rocks have carbon peaks? We don't know until you localize all that information, find out its location. So where do you start? First, you got to localize the spacecraft. So the spacecraft has its own idea of what X, Y, and Z is, and often it's inverted to what we think in terms of mapping sense. That's okay. That's the first part. And then we have to localize all the instruments are. Every instrument has its own coordinate system. Do you want to figure that out? Do you want to dig through the reams of sys's and documents to figure out how to locate the frame on the arm instrument frame onto the rover instrument frame? Usually the answer is no, or at least the scientists say, no, tell me what the result is of all that. So we do this step, so we take the rover base map and we localize it with the ground in situ imagery over the base map. And so then we have we generate science target locations relative to that rover location, and then correct for the roll pitch and all that good stuff. This is basically, so here's the ground map of Mars. We match up an orthophoto of the data. You kind of see some craters match. But, you know, we don't want to stop there. We want to, you know, we have targets that we designate around the rover. We have more high resolution imagery. This is MassCam, registered to NavCam. So now we're getting down to about 1 millimeter per pixel, went from 70 pixels to 1 millimeter pixel. But then we have things like RMI from ChemCam. Now we're getting down to hundreds of microns per pixel. And then, you know, so now we're literally going from space to sand. So we want to be able to locate all these, you know, some data products all the way down to this. And then, of course, each instrument has its own little footprint, and we want to locate those so we understand these two purple APX spots. Are they the same or are they different? Oh, we've got ChemCam laser-reduced breakdown spectrometer spots over one of the APX points. Did we get the same value for silicon or iron? So we can do these cross-science instrument comparisons and see how the values relate or don't relate, or take advantage of some chemistries that one instrument might not be able to cover. So again, we kind of break instruments down to these things that are mass instruments that are attached and then have this azimuth, elevation, and range values for terms of locating on the surface. Things that are fixed to the spacecraft that have no location that we basically move the spacecraft and rotate with the orientation. And then again, these contact science things will allow you to kinematics to actually find the final resting place of a instrument on the surface. So once you do that, you got the little data. What do you do, right? You give it to someone an ArcMap, or you give them the data, and they go, oh, they've got to make the map, they've got to make the symbolization. So we want to provide them a very simple interface. Kind of can. As you saw 2 talks ago, ArcGIS, right? 1,000 toolbars, 10,000 tools. You know how many you need? Probably about 5 for your day-to-day work, right? Zooming, panning, measuring distance, maybe a cross-section, simple queries of data, right? So we've done this for MMJS. So besides the localization of the data products, which we are trying to push out into the PDS, hello, Tom Stein, yes, I hear you talking to me. One, develop a mapping interface for the science team. Again, it's a little bit canned, but it doesn't. You don't have to know, you know, this data set's from CTX, or this data set's from HiRISE, or this is a MassCam image or NavCam image. You just see it and you can work with it. In the center, what's that time? 2 minutes left. Oh, good. 5 minutes until the end. 5 minutes until the end. Okay, sounds good. All right, so at this point, I'm going to jump off. But anyways, so we have this tripart interface where we can both look in the normal kind of 2D map view. We can also look at things in 3D and with the ground view. So I'm going to skip over. Let's see. Okay. So I'm going to show you but this is the one that the science team is currently using. So this is Gale Crater. And we brought in a CTX orthophoto mosaic for the whole crater. They don't need to know that. I know that, but if they want to browse around, they can. Let's see, the traverse starts to show up. More importantly, zoom in more, the HiRISE color layer comes on. They don't need to know it's HiRISE color layer. All they know is it comes in automatically and zoom in. So here's the traverse path. Here's our strategic path as we go up the mound, across the Bear Rubin Ridge, up onto this fan thing. Then we go on farther. These are the waypoints, basically everywhere the rover is stopped. And so the simple thing you might want to do is like, well, what's it look like on the ground? So click on that location in our side viewer. Nice. Here is that view from that ground point. So you have to think about this. So for the tech nerds, so this is Leaflet as a 2D mapping solution. On the left is actually using 3JS and taking the NavCam mosaic in a cylindrical view and wrapping it into a sphere, so you actually remove distortion. So this is kind of actually like it would look like on the surface. You can see things like here, the wheels are actually aligned, and that's the way it is on the surface, right? They're not stretched out. Okay, so that's 2 minutes. I've got 5-ish, 3. Okay. 3 more minutes. Okay, fair enough. But we can go in farther, and we can turn on different layers. So we have ChemCam data. There it is. And so what do you want to do with ChemCam data? Okay, those are locations. But really what I want to do is say, like, what are the values up there? What were the oxides like? And so now I'm going out, pulling in the oxide data, which is kind of quick look products for these points, and we can see what the chemistry is like. Oh, here's calcium. We got pretty high calcium here. We can kind of stack this data. This is a 5x1 chem point, and also look at this one over here. This old whale ledge. So it's showing oxides. Oh, look, there's some high calcium values there. This one, that one has no data. That's fine, that happens sometimes, right? So that's one thing, just these quick look of data, what's going on. But sometimes you want to say, well, I want to look at multiple sets of that data. I want to compare them. So I'm going to add a bunch of this data to a plot. And then I can say, oh, let me look at iron versus aluminum. Oh, there's a very interesting trend here with old whale edge. Not the super analysis you're going to do in PyStat, but a quick look to say, I see a trend, science, or seen this before, let's keep moving. So these all been nice 2D in-ground, and then we can have, I'm going to say, oh, I want to look at the ridge up here, 3D. Well, we can look at this in 3D. So I'm just defining an area. It's actually going up the server, cutting it out. Here's our 3D surface. And we have simple tools for this is no exaggeration, all exaggeration. You can spin it around. We actually have a number of layers that kind of get built automatically to show slope as an overlay, high slopes, low slopes. These are the same vector positions of the rover that we see in the 2D view. So again, making it simple, making it easy to do simple queries. And so I'm just going to show a few things for fun. Monday, I threw in some mercury data just to show that we can do same things. Oh, I actually show off the cross-section tool, so we can make a cross-section across this crater. It's going out to the DEM, the raw DEM sampling profile live. That was not canned. We can do other things like show quick looks for the products. So this is about 6,000 mercury images. I forget what they are. I'm more of a Mars person. But we can again poke into the raw data sets, look at quick look products. We want to show things on a sphere. We can also do things on a sphere, show things in their kind of planetary perspective. Same thing for the moon. These are actually. Okay, I'll stop there. If you have any questions afterwards, I can give you more of the demos or what have you. Thanks.
We have time for a quick question while our next speaker comes up.
Center user, no password.
How's that? Y'all hear me?
Maybe a little higher.
No? Okay, how about there?
Good.
All right, our next talk will be by Bob Dean, talking about mass group stereo analysis and mosaics. Bob?
Morning. So what is MSAM? It's a new PDR test that's just starting up. Heard the funding is at JPL, but I haven't seen it yet, so literally it's starting imminently. It's being run by people from JPL multi-mission image processing lab, seeing people that are camp data and also masking data for ops.
So the point of this is to present this to the planetary science community and get any feedback you guys might have on what you'd like to see, if there's any changes or anything. So what are we doing? We're creating higher order data sets for all available mass cam data. This includes stereo processing, includes train meshes, includes 3 different types of mosaics, which I'll talk about each of them. The basic idea is to process all the data up through PDS release 11. That's what the PDR call specified. We may go farther than that if we can with our funding, and I suspect we will, but since we just started. We're using the same software, same pipeline that we use in operations. So it's well validated and robust. It's the same thing that is generating all of the data that goes out for the nav cams and HAS cams. And also the same thing we process internally for the ops team for mass cam. We expect the data to be available sometime in the fall of 2018. Is when it should be done. Of course, all dates are subject to change. Like I said, we're just getting started. And results will be delivered to PDS. So, what kind of products are we making? First of all, as of PDS release 11, there's almost 12,000 mass cam stereo pairs. So we're talking about a lot of data, and there's a lot more than that in the following that. Rather than go down the list, I have examples of most of these in pictures. But basically, they match the sort of products that we make for the napkins. So, and I should say that the pictures I'm going to show are visualizations of the products we make, but actually quantitative values. So, it's an image full of XYZ points and things like that. So we start with the original image. First thing we do is convert that from the mass cam is sent as a square root encoding, 12-bit to 8-bit compression. So we expand that out back into the linear space. We do stereo analysis, and of course that's the heart of the thing. And from that we generate XYZ data. And so here on the right you can see the red lines are lines of constant X, and green is constant Z. So the blue is actually elevation contours, and the others you can see the XY grid on the data, and that's 10 centimeter spacing. So you can see you can do quick quantitative measurements just by counting the contours. But like I said, there's actual real data here. So if you put, if you had this up in Mars VR, for example, put your cursor on the point, you get the actual XYZ value of that point. There's from there we derive range data, which is simply distance from camera. There's also distance from the rover center. And then surface normal, which tells you the orientation of the rocks. So in this case, the color change to this large, you can see it better on the left, the large rock. It's red on this face and more green on the top, which is how the surface is oriented. There's slope and slope aspects, so this actually tells you, it's a 5-degree slope and it's oriented towards the northeast. There's also a range error product, which will give an indication of what the error is. So there's train meshes, 3D train meshes. This will be in OBJ format, which is fairly widely used. And we think we figured out how to deliver these to PDS4. It's a bit of a trick. It's inspired by some work the Small Bodies node did, and then expanded on by the image node. So we get to mosaics. Like I said, there's 3 different kinds of mosaics. First one is co-registered mass cam and nav cam. So the idea here is if you have a mass cam observation, and this happens to be a drive direction mosaic where they take 5 frames in the direction they want to drive. You can combine those with the nav cam to get a more full understanding of the area and get geological context. These are actually co-registered Um, it's not perfect because parallax, but it's pretty close. And so you can see this is a global on the edges. You get full res masking, and at the same resolution, the nav cam, of course, it's over res, so it's blurry, but as a context. So it's cylindrical projection, and you know, a question for the community is how much nav cam context do we want around these images? You know, we could do a full 360 at each location, but if you have two masking 100 frames, you know, it's a gigapixel for 2 frames. That's a lot of data. So, if you have any input on that, on how much, you know, as you're looking at the geology of these frames and trying to figure out what they are, how much context is needed. Next thing is stereo mosaics. So we're going to make this from as many data sets as possible. Not conducive to stereo viewing, just because how we are wired. But both is color stereo and red, blue, and glyph. So if you have, you know, specialized hardware, you can see actual color stereo. If you don't, you put on red, blue glasses. Orthorectified mosaics of DEM. So we take all the XYZ values and the that goes with it, and create a true overhead view of the terrain, orthorectified projection, and then there's a DEM that goes along with this. So, and these I'll also be using the places data to give us a localization. So we'll have this context, you know, like latitude, longitude, corners, and things like that. So data size, there's, like I said, this is as of PBS release 11. Stereo products, that's 13 terabytes. All told, we're expecting about terabytes of data here. And about 16,000 hours of compute time on Amazon Cloud. So this is a significant effort. Jim Bell at Arizona State also has a PDAR from St. Paul starting now also that's doing radiometric correction of the mass cam data. So we've already talked with him and we're going to work together to take his radiometric corrected results and incorporate them into our mosaic submissions. So those results don't affect the stereo processing, but that'll result in a much better, much nicer mosaics and mesh products. So it's a nice synergy there. Results will be delivered to PDS, in PDS4 format, of course. But they're also compatible with what we're doing on MSL already. MSL is a PDS3 mission, okay, for heritage. So the same basic image file that we deliver for our nav cams and hand scans, ODL dual labeled image, and then there'll be a PDS4 detached later. So if you have software that works with MSL data, it should work just fine with this. Software that works in PDS4, I want to know about it, but no, if you do, if you do, then it'll work with this as well. Now, another question for the community, do we actually need a PDS3 label? So it can't be an official PDS3 product because PDS is not accepting new PDS3 data, but it would be syntactically, exactly the same, semantically the same. There is already an ODL label, which is very similar to the PS3 label that's attached. And this may be sufficient, but if anyone has a really strong need for an actual but not validated PS3 label, please let us know. So PDS peer review, we're expecting around the end of this year. And of course, dates may change. But we're looking for peer reviewers. If anyone wants to participate, please contact us and let us know. And run out of time. Through the beat. So if you have any feedback or anything, please let us know. That's the and the full team. Actually, several of these people are here this week. Sterling, Nick, Adrian, Costine, and Amy are all here, as well as Ray Everson and Darby Oliver. science consultants. So, questions?
So I have a couple questions. Looks like a great project. I'm happy to see it funded. How are you planning to do the horizontal registration? Are you going to try to tie it to what context? How do you feel about how accurate you can get horizontally?
In XY?
Yeah.
In terms of frame to frame within Mosaic, that's within a mesh. We're essentially using the raw point, so we're not anticipating on correcting that, but the pointing is pretty close. So we don't anticipate there's a lot of errors there. I mean, when you do the meshes for the nav cam, there's no correction in that way. In a larger sense, there's localization. So we do know where the rover is based on Jim Parker and Michaela's work to localize the rover, and so we'll incorporate that in the labels and say where the orbitals are.
I guess as a more is merrier. I guess I would have that if you're willing to support PDS3, you might as well. Time consumption. But the last question really is, do you guys plan to? I mean, we saw Fred's tool and then GIS, great for rover data. Do you guys plan to have an idea of incorporating it in some kind of tool like that? Your data to make it more accessible.
Yeah, part of the proposal actually is to update Mars Viewer tool to read this data. And I see Fred every day. I'm sure he'll make use of this as well.
Okay, good to hear.
Thank you, Bob. Give your lab mic to Moses. I am. I'd like for you to get mic'd up. You are. Why didn't you mic attached? So Moses Malazzo is going to talk to us about archiving GIS data products in PDS.
Thanks, Russ. Go right ahead. Most of you here know what is GIS, so I'm going to skip through the recap slides pretty quickly. GIS is a system capable of capturing, storing, displaying geographically referenced information. I'm stealing a line from Trent here. The bottom line is that GIS is a framework for the science of where. Where are things? How are they spatially related? How are they geographically related? What does GIS provide? Complex analysis is enabled, reuse can be enabled, and cooperation between teams for doing science. A GIS language called GML, the Geography Markup Language, is an XML grammar defined by the Open Geospatial Consortium, graphical features in the GIS. And GML is a modeling language for the GIS and is an open interchange format for GIS software applications. It includes many primitives, most primitives that are included in other GIS packages, and is an ISO standard, an international standards organization standard that was approved in 2007. The most recent approval was in 2007, so it's a pretty stable standard as well. It has been approved by the Library of Congress for archival of GIS products and is also used by the FD and National Spatial Data Infrastructure for archival of GIS products. So why GML for PDS4? Why GIS for PDS4? Right now, you cannot archive a GIS product in the PDS simply for a number of reasons that have to do with compatibility, binary file formats, and etc. GML is available and is a standard stable language and is supported by many major and minor GIS packages. The GIS products that are being delivered to the USGS regularly do not fully meet archival standards at this time. We are working to improve that, but at the same time, we're working in parallel to improve PS4 archival. Why should we not use GML for PS4? Everybody asks me this question. ArcInfo shapefiles are the most commonly used GIS that I know of in planetary applications. Those shapefiles are also a standard for the shapefile format is open, but parenthetically it's a proprietary and binary format, which means you have to have specialized software. You can't write your own software. You can't use or new software packages to access those shapefiles without going through some hoops. Those ArcInfo shapefiles are supported by all major and minor GIS packages, similar to GML. Shapefiles are easier to generate for most users, and this is probably the #1 reason not to use GML for PS4 archival is because we're already generating shapefiles, and why should we have to now generate another set of GIS package files? And another argument for not using GML and for using ARC is that USGS Astrogeology already archives ARC projects. However, those projects, like I already said, are not yet fully compliant for deep archives. The projects archived with USGS are not searchable within the context of the PDS because they are missing important metadata that are expected in PDS4 archives, and therefore, when you search for data with the PDS, you will not find any of those GIS packages in US Geological Survey. And shapefiles are a proprietary format, which means the community has very little control over the future of the shapefile format decisions and whether or not they will remain compatible with the planetary sciences community. Whereas the OGC has demonstrated its willingness to be open to updates and corrections to their standards for the use of the planetary science community. So let's go into what is GML exactly. GML is a language that's based on XML, and in this slide I show a hierarchy of a GML product which has approved tags and attributes, and you can view these in a number of different pieces of software, whether it's looking at spatial information itself or looking at the structure of the GML file. And that's useful for software developers, that's useful for planners for how to create archive projects and or incorporate GML into other software projects that don't yet use it. The documents that are archived with the USGS can still be archived under PDS, so there's no change there. There would be no change to the raster layers. Those can easily be viewed with PDS4 viewer tools and can be archived utilizing the raster archival requirements from PDS4. Most of the other or all of the other files conform to PDS4 standards already. So the files that you're delivering to Astrogeology's GIS archive, already the files themselves conform, we just don't have the labels that conform to the PDS4 standards. So most of the layers, the vector layers to the PDS4 would be GML files. They're plain text utilizing the XML structure. Base maps and other raster images, like I just said, can be archived as PDS4 compliant images. Browse products can be archived in similar formats that are PDS4 approved. And document products such as project description, published papers, published maps, and etc. can be text or PDFs, which are all PDS4 file formats. So the only thing that's really needed to be able to archive your project in the PDS4 is a conversion of your vector layers to GML and the writing of the PDS4 XML labels for all of those products that come out of your GIS package. And the plan is, over the next 6 months or so, to write Python plugins for QGIS and for ARC to do this conversion for you, so that for the most part, you will only have to click PDS4 and you will get a PDS4 compliant project ready to deliver to the PDS. Very quick. Any questions?
I was under the impression that XML was not legal as a data file format for PDS. Is that question wrong, or is it a special case, or what?
Your impression is not wrong, and your impression is wrong. So the issue is XML files that end in .xml are expected to be PDS4 descriptors. So those are the labels that are expected. So anything that has a .xml extension is expected to be part of the product description, not part of the product. The GML files themselves are structured as XML, but they are .gml file extensions, and so they're plain text, and you can reference those using the XML labels for the PDS4. Kevin?
Devin Bird, University of Tennessee. I think this probably isn't a question for anyone in this room. I think it's probably a question for program managers. But I'll just throw it out there anyway. So for those who might be writing, say, PDARTs this summer, or other proposals this year to produce maps, for our data management plan, do we say we're going to put it on the annex, and then when the capability to put it on PDS4 comes online, we're going to do that? Or do we not say anything about PDS4 so that we don't throw off the reviewers who won't have heard about this before?
Well, you will be, part of the review now is whether or not your data management plan produces products that will be archived in a PDS4-like archive. So you need to mention how you're going to archive those products. PDS4 or not is up to you as a proposer, but you have to otherwise mention what the archive is and describe that archive in a way that makes it clear that it is PDS4-like.
Sure, I understand that, and that's why I mentioned the annex that we talked about 2 hours ago. So.
Right, so working towards is once we have finalized how this GML archive will look and what the standard labels will be, we will be able to include that in that letter of support that you need to get from whichever PDS node you intend to archive with. And at that point, and I can't say that it's going to happen before PDARTs are due, but at that point, that letter of support, if you're going to archive a GIS product, you make sure you mention that in your email to the PDS node lead, and that letter of support should then mention that this kind of GIS product is an allowed archival product.
So since neither Moses nor I are actual project managers, I'll give you a different perspective. This tool that will convert it into a PDS4 format will not be available by the time PDARTs are due a month from now.
No, it will not.
So that means that if your planned output for a PDART is a shapefile, you cannot archive it as proper, because to do so, it needs to be in a PDS4 format. So you must find another equivalent archive to archive your shapefile into. PDSNX is a fine example of one that is PDS equivalent for shapefiles. There may be others.
What's your time frame?
I'm looking at maybe 6 months.
And you think it'll have PDS4 approval?
I think it'll have PDS4 approval before that. I'm looking at software plugins written, maybe not fully tested, but written for QGIS and for ARC. by that time.
Thank you.
So Moses, I have a question for you. So I understand how this works if you have a shapefile or you have a raster stuff or a project. What if you have a mosaic or a terrain model that is a map, it's projected, archived out to PDS as a raster image with labels that talk about its projection? Or would you also?
I think that would be up to you as the data provider. Do you want to include metadata with that product? If you want to include your GIS metadata, such as all the details about where you got that went into that mosaic or whatever, then it would make sense to archive it as a GIS product. If you have a paper that goes along with that, and those are the two things you have the mosaic and a paper, then archive those as your product. I think it's on the data provider's expectations of how these data will be used in the future.
Okay, thank you. Any other questions for Moses before lunch? Thank you for your attention. Have a great lunch back here at 1:30.
No?